We are honored to have with us our beloved director, NIT Warangal, Professor Bidyadhar Subudhi, with us. Welcome you, sir. We also welcome Professor S.S. Srinivas Rao, sir, Dean IRAA, NIT Warangal. Thank you, sir, for your presence. We also have with us the head of the department, Professor N.V. Srikant, sir. Welcome you, sir. And then let us all get together to welcome Professor Rukmi Datta from University of New South Wales, Sydney, Australia. Thank you, ma'am, for coming all the way here. I now request all the dignitaries to kindly occupy the dais. I request all to raise for the national song.
Vande Mataram, Vande Mataram, Sujala Sukhada, Malayaja Sheetala, Sasya Shyamala Mataram, Vande Mataram, Shubhrajyosna Pulakitayamini, Pullakusumita Drumadala Shobhini, Suhasini Sumadhura Bhashini, Sukhadam Varadam Mataram, Vande Mataram, Vande Mataram.
I now request the dignitaries to proceed for lighting of the lamp.
असतो मा सद्गमय, तमसो मा ज्योतिर्गमय, मृत्योर्मामृतङ्गमय। ॐ शान्ति शान्ति शान्तिः। असतो मा सद्गमय, तमसो मा ज्योतिर्गमय, मृत्योर्मामृतङ्गमय। ॐ शान्ति शान्ति शान्तिः। असतो मा सद्गमय, तमसो मा ज्योतिर्गमय, मृत्योर्मामृतङ्गमय। ॐ शान्ति शान्ति शान्तिः।
I now request Professor T. Vinay Kumar to provide an overview of the GIAN course.
Yeah, good morning to all. Respected Professor Bidyadhar Subudhi, Director of NIT Warangal, Professor S. Srinivas Rao, Dean, IRA, next Local Coordinator for GIAN, Professor N.V. Srikant, Head of the Department, esteemed faculty, Professor Rukmi Datta from University of New South Wales, Australia, participants and colleagues, it is my pleasure to welcome you to the inaugural of the GIAN program on permanent magnets, synchronous motors for transport electrification. See, transport electrification, particularly in automobiles and aerospace application, demands high efficiency and high dynamic performance. See, if you want to improve the efficiency, you need to take care about design part. If you want to improve the dynamic response, you need to take care about the control point. So, particularly this workshop concentrate on how to design the permanent magnet synchronous machine for automobiles as well as aerospace applications, right? And also we'll try to discuss about the how to develop the mathematical model to extract the characteristics of the PMSM machine, right? Based on the characteristics, if you want to improve the performance, right, you need to adopt advanced control methods. In this session, we'll try to focus on director control method, field orientation method, and model predictive control method. At the same time, see, this course particularly will focus on fundamentals, practical sessions also on how to design the PMSM machine for automobile application as well as aerospace application, right? Next, one more important thing is we are honored to have Professor Rukmini Datta, particularly she is expertise in design of the magnetic circuits in automobile as well as aerospace application, right? Definitely she will guide us through this journey, right? I thank Professor S. Srinivasrao sir and Professor N.V. Srikant sir for their support, continuous support and guidance to organize this program. And also I encourage all participants to engage actively and share ideas. Thank you, and I wish you all the enriched experience.
Thank you, sir. Well, yesterday was the smallest day of the year, but I'm sure as the days go by, the days would get smaller for the participants as they would be, busy engrossing in capturing the knowledge that would be given to them. Thank you, sir, for that wonderful introduction. I now request Professor N.V. Srikant sir to provide an overview of the electrical department.
Good morning to all of you. Respected Professor Rukmini Datta, School of Electrical Engineering and Telecommunications, University of New South Wales, Sydney. Respected our beloved Director, Professor Vidyadhar Subudhi, Professor S. Srinivasrao, Local Coordinator, GAIN Programs, and this program coordinators, Dr. Vinay Kumar and Dr. Shivakumar, participants of this GAN program, colleagues, ladies and gentlemen. It gives me an immense pleasure to introduce about our department to you all on this inaugural function of this GAIN program on permanent magnet synchronous motor for transport electrification. The Department of Electrical Engineering is one of the oldest departments of REC Warangal, National Institute of Technology Warangal. Earlier it was known as Regional Engineering College Warangal. It was established as a major department of the institute. Since its inception in 1959, the Department of Electrical Engineering has been actively engaged in teaching and research and in the diverse fields of electrical engineering. At present, 31 plus 1 new faculty has joined. Around 32 faculty members are working in the department. Faculty have expertised in various fields of electrical engineering such as power systems, powertronic converters, drive systems, smart electric grid, control and automation, control of special machines, design, renewable energy systems, converters, LED lighting systems, multi-level inverters for opening winding induction motors, applications of powertronics to power quality improvement and industrial drives, hybrid energy storage systems, DSP control drives, artificial intelligence techniques, applications to electrical engineering, etc. The Department of Electrical Engineering offers BTech program in Electrical and Electronics Engineering, MTech in Powertronics and Drives, Power Systems Engineering, Smart Electric Grid, and MTech in Control and Automation. just started in this academic year, one semester already over, and PhD in all the major fields of electrical engineering specializations. We also have self-finance programs in MTech, PG diploma, and also in PhD. Now we also have at present 136 students admitted through JEE for our BTech program, and around 95 students through GATE in MTech programs. At present, around 100 research scholars are working for their PhD degree in our department. Many research projects sponsored by various agencies, MOE, MHRD, Imprint, Spark, DST, SCRB, CPRA are being executed to the tune of 650 lakhs. Very recently, DST FIST project cost more than 1 crore is sanctioned to the department. At present, 9 junior research fellows are working for execution of this project. Department has state-of-art equipment such as programmable DC power supplies, programmable solar simulators, high-end mixed signal oscilloscopes and digital signal oscilloscopes, multi-level inverters, lab view software and hardware development kits, DSP kits based on 2407, 2812, etc. We also have OpenRT, rapid prototyping systems such as DSpace, Microlab, etc. We also have a full-fledged smart electric grid lab funded by Hitachi Energy India Limited. All these equipments are purchased from grants released by MHRD to equipment various sponsored research projects. The department has a strong industry interaction and has been involved in constantly handling various consultancy projects for various industries and lift irrigation projects of Government of Telangana and Andhra Pradesh. Department has an MOU with Central Power Research Institute, Bangalore, ABB, Power Products, Hitachi, India Limited, Power Grid Corporation, Power System POSACO, and now as known as Grid India to carry out collaborative research projects. Department participates in the student exchange program with IIT Delhi. Student support activities, technical support through Electrical Engineering Association, technical support through IEEE student branch and Women in Engineering, student mentorship, industry visits, industry lecture series through EEA, and in curriculum related courses are actively engaged in our department. Overreach activities, prestigious faculty development program and training programs such as GIAN and all as sanctioned to the department sponsored by Government of India under various prestigious schemes, especially GIAN, ATAL, Spark, E and ICT, MIT, TLC, NIT, Pandit Madan Mohan Malavya National Mission on Teachers and Training, etc. Now, we also have self-finance STTP by the faculty of department through which our department faculty are contributing to improve technical education in various domains of electrical engineering community in the region and across the country as well. Apart from this, department faculty actively contributing towards various academic and research activities to community of technical education. MTech SCG program was started in academic year 2020-21. It's going on very well with high placement record. We also have towards our placement record, our BTech students are placed more than 90%, and all our MTech programs are also going on very well in their placement record. The department also started working for industry collaboration for development in the research and in the research. The department having good placement record and heritage for few of our alumni occupying positions in India, Indian Administrative Services, IES and CEOs of the companies. Now with this brief about the department, I welcome you all to this GAIN training program on permanent magnet synchronous motor for transport electrification. Thank you all.
Thank you, sir. We are really proud to be associated with the Electrical Engineering Department. I now request Professor S. Srinivas Rao, Dean IRA and Local Coordinator for GIAN Programs to address the gathering.
Welcome and good morning to all of you. Respected Director Professor Vidyadhar Subodhi, Foreign Professor Rukmi Datta, School of Electrical and Telecommunication Engineering, University of New South Wales, Sydney, Australia, and Head of the Department, Professor N.V. Srikanth, Course Coordinators T. Vinay Kumar and G. Shivakumar, and my dear participants and faculty of Department of Electrical Engineering and retired faculty and the other faculty members of the institute. Good morning and welcome to all of you once again. So myself, I am Professor Srinivas Rao, working in the Department of Electrical Engineering, and I am also Dean International Relations and Alumni Affairs and local coordinator for this GIAN and Spark programs. So this Dean International Relations and Alumni Affairs Office look after the alumni chapters of all the graduates from this institution. There are around 42,000 plus alumni are spread across the world, and we have 22 alumni chapters in India and 7 alumni chapters across the world. And with relation to related to international relations, this office is looking after the these programs, GIAN Global Initiative for Academic Networking and Spark Scheme for Promotion of Academic and Research Collaboration, and UK India Education and Research Initiative, Heritage, BRICS, DAD, MITAX, and so many other programs. Now, this past 1.5 to 2 years onwards, we are very much actively working under the dynamic leadership of our director, Professor Vidyadhar Subodhi, to make our institute an international significance. You all know that NIT Warangal has a sufficient significance in the country, and now we are seriously struggling to get international collaboration for MOUs related to graduate exchange programs as well as student exchange programs and faculty exchange programs and international collaborative projects. So I thank our director for encouraging and dynamically involving in increasing the institute reputation towards international level. So about this GIAN, this was GIAN is initiated by Government of India in 2021, aiming at tapping the talent pool of scientists and entrepreneurs internationally to encourage their engagement with the institutes of higher learning in India, so as to augment the country's existing academic resources, accelerate the pace of quality reform, and elevate India's scientific and technological capacity to the global excellence. The proposed objectives of GIAN are to increase the footfalls of reputed international faculty in the Indian academic institutes, provide opportunity to Indian faculty to learn and share knowledge and teaching skills in cutting-edge technologies, to provide opportunity for Indian students to seek knowledge and expertise from reputed international faculty, to create avenue for possible collaborative research with international faculty, to increase participation and presence of international students in the academic institutes, opportunity for the students of different institutes and universities to interact and learn subjects in most advanced areas through collaborative learning process, provide opportunity for the technical persons from Indian industry to improve understandings and update their knowledge in the relevant areas, motivate the best international experts in the world to work on problems related to India, develop high quality course materials in advanced areas in the form of video recording and live webcast, so that it can be used by large number of students and faculty in the country, to document and develop the new pedagogical methods in emerging topics of national and international interest. With these objectives, the Global Initiative Program was initiated, and the proposals were submitted from the institute, and so many proposals we got, and all the courses are running towards achieving these objectives. So NIT Warangal has successfully completed GIAN Phase 1, Phase 2 and Phase 3 programs. This is Phase 4 program is running now. In 2015-16, 27 programs were sanctioned in GIAN Phase 4 with 1.87 crores. In 2017-18, 41 courses were sanctioned with a budget of 2.48 under Phase 2. And in 2019-23, 21 courses were sanctioned under GIAN Phase 3 with a sanctioned amount of 1.41 crores. In 24-25, present scheme, 22 courses were sanctioned till now with a budget of 1.4 crores, and 9 courses all are still under review. We are expecting that those courses also may be getting approved. Our special thanks to Dr. Anil Agarwal, National Coordinator of Global Initiative for Academic Networking at Hyderabad, and IIT Hyderabad administration for speeding up of the review process and sanctioning the GIAN Phase 4 courses. Till now, 6 courses were successfully completed in Phase 4. This is the 7th course. Another 15 courses are yet to be completed before June 2024. In all 4 phases, total sanctioned courses to each department is civil engineering 27, mechanical engineering 16, chemical engineering 14, electrical 13, ECE 12, mathematics 7, computer science 7, chemistry 3, MME 2, and physics 3 courses were sanctioned till now. Total number of 49 faculty members are collaborated with NIT Warangal under GIAN course from different countries like UK, USA, Australia, Belgium, Israel, Canada, Singapore, Germany, Italy, Japan, Malaysia, Europe, Norway, Portugal, Romania, Russia, Slovakia, Sweden, Taiwan, Greece, Denmark, France, England, Scotland, Finland, and Middle East. In the recent past, for these GIAN and Spark programs, past 50 years, many international faculty visited, and all our faculty as well as students and participants for various courses got a lot of exposure by interacting with international faculty physically. Some of those international faculty visited in the recent past 50 days are Professor Rahul Rai, Department of Atomic Energy, Automotive Engineering, Clemson University, USA, Professor Alfred Kalyanapu, University of Tennessee, Professor Tanya Datta, University of Tennessee, USA, Professor John Shivarji, University of Tennessee, USA, Professor Vijay Raghavan, McGill University, Canada, Professor Maxim Shatov, Institute of Cytology of Russian Academy of Sciences, Russia, Professor Shrikant Joshi, University of West, Sweden, Professor Channapat Paniswas, Queen Mary University, London, Professor Indrajit Chaube, University of Connecticut, USA, Professor Tarun Ratnaraj, University of Edinburgh, UK, Professor Tarun Ratnaraj, University of Edinburgh, UK, Professor Rahul Jain, National University of Singapore, Professor Ranjit K. Soman, Delft University, Netherlands, Professor Leon, University of Twente, Netherlands, Professor Israel Cohen, Technion University, Israel. So I hope all the participants, by interacting with foreign faculty, Professor Rukmi Datta, will be getting more knowledge in the topic of permanent magnet motors for electric transportation. We all know that the now present era for transportation is electric vehicles. So as nationally as well as international policies were already derived, urban mobility must be of electric transportation. That may be two-wheelers or four-wheelers or different type of variety of vehicles for various purposes. So we all know that the significance of permanent motor is permanent magnet motors are more, particularly permanent magnet synchronous motor significance is more in the transportation, electric transportation systems. They may be of ground fixed drives or ground movable drives, water fixed drives, water movable drives, or any type of drive system. A motor is essential for that motor. So efficiency is important. All these things will be dealt very much clearly with these 5 days by Rukmi Datta. I welcome to India and welcome to NIT Warangal for her. By discussing with her, we will be getting a lot of information. So I thank all the participants for showing interest to come here and physically attending the courses. Special thanks to our director, Professor Vidyadhar Subodhi, for his constant and continuous encouragement. We are able to make our institution as an international reputation. So thank you one and all.
I now invite Dr. G. Shivakumar to introduce Professor Rukmi Datta.
Yeah, thank you, Dr. Altaf. Good morning, everyone. It is my honor and privilege to introduce our distinguished guest and international speaker, Professor Rukmi Datta, for the inauguration of the GIAN course on permanent magnet synchronous motor for transport electrification. Professor Rukmi Datta is an accomplished associate professor in the Energy System Research Group at the School of Electrical Engineering and Telecommunication, UNSW, Sydney. With an illustrious academic and professional career, she earned her PhD in Electrical Engineering from the UNSW in 2007 and a BA in Electrical Engineering from Assam Engineering College, Guwahati University, India in 1996. As a senior member of IEEE and an active contributor to several IEEE societies, Professor Datta is widely recognized as an expert in the design and control of innovative permanent magnet machines and high performance drive systems. Her research focuses on transformative applications in electric vehicles, renewable energy, and distributed generation. Over the years, she has secured over $10 million in research funding and has published more than 120 peer-reviewed papers, a scholarly book, and several book chapters. Her groundbreaking work has also resulted in patents in the field of high-speed permanent magnet machines. Professor Datta has extensive teaching and leadership experience, having supervised over 20 PhD students and served as a postgraduate research coordinator at UNSW. Among her numerous awards are the IEEE PLS Region 10 Distinguished Lecture in 2021 and the UNSW Outstanding Supervisor Award from the Student's Choice in 2018. Her active participation in global initiatives through keynote speeches and webinars reflects her dedication to advancing energy systems, research, and fostering innovation. Let us warmly welcome Professor Rukmi Datta, whose insights will undoubtedly enrich our discussions and inspire us all. Thank you. I invite Professor Rukmini Datta to address the gathering.
Good morning to all. Respected dignitaries in the stage, faculty members and participants. First of all, I want to thank NIT Warangal to host me here. GIAN program is, I think it's a wonderful program to have interaction with international academics, researchers, and Indian researchers. This program, the one that we are going to run, as previous speakers already explained, that transport electrification is one of the emerging field, which has actually bring the electric motor drive research to focus. I believe in recent times in India, we hardly saw any research on electric machines, but it's coming back with the electrification of transport. So when we said electrification of transport, it's not just the electric car, it's also aerospace. And this field of research is just actually beginning. So only recent times people are saying that electric vehicle technology we can compare with what was in 1940 the internal combustion engine of our current car. So in 100 years, the internal combustion engine has come to this level. And so there is plenty of work to do or to research on this field to bring the electric powertrain of cars and even aircraft, etc., to bring to a level where the internal combustion engine is at current stage. So that should motivate young researchers. This course actually we are running for the second time. I ran it in 2022 in another institute, but because of COVID it was online. So I thought I didn't have the interaction that I wanted to have with the Indian researchers. I hope that this time I will have that opportunity, and I would like to make this course more interactive and hope it will help someone who want to go to this field as a starting point. I thank everyone again for hosting me, and I look forward for the next 5 days for the interaction. Thank you.
Yes, ma'am. As correctly pointed out by you, one of the objectives of GIAN is to have a good interaction with the foreign faculties. Thank you, ma'am. In 5 minutes also it was too meaningful. We could learn something again there. So you gave us the targets. I now request our beloved director, Professor Bidyadhar Subuddhi sir, to kindly address the August gathering.
A very good morning to everyone in this GIAN program. I take this opportunity to join with the Department of Electrical Engineering to welcome our foreign faculty, Professor Rukmi Datta from School of Electrical Engineering and Telecommunication, University of New South Wales, Sydney. And I am glad that the Dean Alumni and International Relations, Professor Rao, has mentioned the remarkable achievement of NIT Warangal in terms of making it visible across the leading institute of the country in terms of securing a high number of grants for GIAN and Spark, which are the true indicators for the international collaboration. And I must congratulate the Dean for taking it forward and the faculty colleagues to working hard to make it a grand success for NIT Warangal. At the same time, the head, Professor Shikant, has given a very, very extensive overview of the department. I'm quite glad that the department is doing wonderful in terms of several interesting programs to run successfully, and also the placement record, and also the kind of laboratories and organizing such programs for the benefit of the nation. Incidentally, I'm an electrical engineer. So to me it appears that, okay, what Madam Datta has rightly mentioned, that always there is a change necessary. Because if you see in the global market today, particularly in the Indian scenario, if I look up, so people are more, skeptical about the opportunities of the employment for the electrical engineers. But if you see, now this creates a new avenue in terms of more application of the electric motors in several, areas. For example, if you talk about either the space vehicles or underwater vehicles or the surface vehicles, whatever you talk about, where there is a drive motor is essential. And then when you talk about a drive motor, depending upon the characteristics and the source, so obviously there is a lot research and the company, the industry endeavor necessary for the design using some kind of standard software, and also to verify, to optimize for several aspects, and to have the coordinators have rightly mentioned, Professor Binoy Kumar and Professor Shiv Kumar, they have rightly designed the course. I have just glanced it, like the design aspect using the software and the different control techniques. So it is well planned, and I believe it is a very useful program to attend. And I urge upon all the delegates, all the participants for this program to take the maximum benefit in learning from the well-designed GIAN program over here. And not only that, please find some time to go around the department, different labs, not only the machine labs, and also try to explore the opportunity, how best you can collaborate with the faculty of the department in future. Say, for example, you can have a joint project, a joint startup, or a joint transfer of technology, or maybe anything else you can think of where you can certainly make a good start from here. Now, coming back, why it is necessary, this GIAN program, the Spark program, the research, the sponsored research, technology transfer. If you go back the history years, we are only concerned about the teaching. And that's it. So if you go on only the teaching that is in the book and you go and teach, nothing happens. If you research, you go for a sponsored research, that will change the scenarios. I am talking of the today, whatever you are, it is because of the research. Like if you talk about some 10, 15 years ago or 20 years ago, when you go to either a railway station or to a bus stop or to an aeroplane, you find the elite class people having a mobile phone in their hand. Why it is? Because it is very expensive. And what made the cost down? It is the research totally. So similarly, research is essential. And whatever today you see, it is all possible because of the strong R&D necessary. And I'm quite glad the country like us, the India, has made a very big progress in terms of reaching out to this ANRF, where now the possibility of funding the the young faculty and the middle level faculty is quite enormous in terms of making good progress towards transfer of technology. For example, different tier level you can think of. It's not just for a promotion that the sponsored research is necessary. It is also necessary to make you more visible across the peers how best your ideas, new ideas. Because if you tell, because if I see that when some 10 years ago you would tell somebody I'm doing on a research on DC motor, so then people think that DC motor is oversold, oversaturated. Then what should I do? Now you see it is opening up because new softwares, new techniques, new optimization techniques, and machine learning or quantum computing, all of them are now applied to the machine design. So obviously research is very, very essential. So these kind of, workshops or the programs will open up the new avenues for the delegates to think of and to go along. Because if I just recall maybe few years ago when the program like this, I just recall some 25 years ago, when the professors from other countries, they came and gave a deliberation that one day you will see your watch will contain everything, no need of a camera, no need of a mobile phone. Now I could realize now in my hand I can do the same things. That's a reality. So the visionaries in research, they predict what should be in future. And I believe the electrical engineering has a big scope in terms of the industry need, in terms of the transportation, particularly the motor and drives. And magnetics one part of it, electromagnetic compatibility. So therefore, I urge upon again all the delegates to make it more meaningful by attending, discussing, disseminating whatever way you can to the extent possible, and to have and I'm glad that the coordinators have rightly included the hands-on practice in the lab that will definitely augment the learning in a more meaningful manner. So with this, I once again congratulate both the coordinators, Professor Bino and Professor Sivat, for making it to happen here in NIT Warangal, and wish both the coordinators and the department to run it successfully. And not only the academic participation, I believe your stay in the campus NIT Warangal should be more enjoyable. And I believe after the end of the course, you will carry a good kind of message for us. I trust that you will be our brand ambassadors in propagating the message. See, here is an institute which not only conducts the GIAN program, but that also keeps the avenue open for the collaboration in future occasions to come. Thank you very much.
Thank you, sir. You have always been encouraging us, and your encouragement is the backbone of our progress. Thank you very much, sir. I now request Professor Bidyadhar Subudhi sir and the dignitaries on the dais to felicitate our foreign expert, Professor Rukmi Datta. Thank you, sir. I now invite Dr. D. Srinivas Rao, sir, to present the vote of thanks.
Thank you, Altaf. So good morning, everyone. It is my honor and privilege to deliver the vote of thanks at this inaugural function of this GIAN course on permanent magnet synchronous machine for transport electrification. So on behalf of the Department of Electrical Engineering, NIT Warangal, I extend my heartfelt gratitude to all those who have made this event possible. So first and foremost, I express my sincere thanks to Professor Bidyadhar Supudi, Director, NIT Warangal, for his inspiring address and unwavering support for organizing this GIAN course. Sir, your words have set the tone for what promises to have a highly enriching and impactful program. So I profoundly grateful to our esteemed international faculty, Professor Rukmi Dutta from the School of Electrical Engineering and Telecommunication, University of New South Wales, Sydney, Australia. Your expertise and willingness to share knowledge with us are invaluable. We eagerly look forward to your sessions in the coming days. A special thanks to Professor S. Srinivas Rao, Dean IR and AA and local coordinator of GAN programs, for his encouraging address and continuous guidance throughout the planning of this course. I also extend my gratitude to Professor N.V. Srikanth, Head of the Department of Electrical Engineering, for his insights and steadfast leadership. So my heartfelt appreciation goes to the course coordinator, Professor T. Vinay Kumar and Dr. G. Shivakumar, for their meticulous efforts in organizing this program and for giving us a comprehensive overview of this course and a beautiful learning experience. So I would like to thank Dr. Altaf Badr for gracefully welcoming the dignitaries and initiating the program, as well as the entire faculty, staff, and students of the Department of Electrical Engineering for their efforts and enthusiastic participation. So finally, I thank all the distinguished guests, participants across India, and attendees for taking the time to join us today. So your presence motivates us to continue hosting such meaningful academic endeavors. So thank you all, and have a wonderful day ahead, and thank you.
I now request all to raise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
We would request the dignitaries for a group photo. The participants are also requested to come.
Okay. this is gone. Okay, we start. Yeah, you can. Worst case, we will use another. I'll just take the USB. Okay, good morning. So we'd like to make it interactive, so please feel free to stop me and ask questions whenever, okay? Just raise your hand, okay? We'll start from quite fundamental and then we'll build on to a more advanced one. First 2 days will be more on the design and the next 2.5, and then other 2.5 will be on control, modeling, etc. It could be some of you who are doing PhD, you may find it like fundamental, but for others who are not familiar with the field, maybe it is useful. So we want to bring everyone to the same stage. That's why sometimes we'll go to very basic as well. Okay? So before I start, I just want to introduce you to my university. I think some of you may not know it. It is duplicate. I did. So it was coming, right? There is something with that. So if you touch it, still not coming. So it's something to do with that power switch. Yeah, it's all right. Okay, so I just wanted to introduce you to my university. So since you may not know, some of you may not know, the University of New South Wales, in short form, it's UNSW. Because we are in Sydney, we also have a campus in another capital city, Canberra, but this is the main one is in Sydney, so we call it UNSW Sydney. We were, like last 2 years, we are QS World Ranking 19th and higher education ranking 84. Sometimes it varies, like last couple of years it's varying from 84 to 74 within that 10 ranking in Times higher education ranking. It's one of the largest university in Australia, so we have nearly 60,000 students because we have engineering, we have medicine faculty, law, humanities, all the things. Engineering is one of the biggest, so we have nearly 10,000 students in engineering, and 2,900 academics. So in the middle of the campus, we have the electrical engineering. You can see that the electrical engineering building there is newly renovated. We are number 1 in Australia, electrical engineering, one of the biggest. And we have all the core electrical engineering research and teaching in our school, control, quantum engineering, microelectronics, electronics, power engineering, under power engineering, power electronics, electric drive systems, pure power system. Under microelectronics, we have just analog digital electronics, including the very like most recent one, quantum engineering. And so the New South Wales is actually the name of the state, or one of the state in Australia. It's in the east coast of Australia. Sydney is the capital, so that's why the name is on the name. The university name is on the name of the state. So UNSW. That's why University of New South Wales. Our campus probably is like area-wise will be smaller than probably NIT Warrangul, I think we are much more compact. A lot of buildings all close by. But we are also very close to some of the well-known tourist spots, such as Bondi Beach, only 4 kilometers from our campus, 3.6 kilometers for Marubra Beach, and so on. So if you ever visit, our university campus, you will have also opportunity to go to these places. Next, I would like to show you a few facilities that we have under the this machine, electric machines and drive and power electronics lab. So first one in your left-hand side is the wind energy system, an emulator and a generator, direct drive generator of 54 pole. The middle, you can see a electric vehicle traction drive motor and its drive system. And last one, you can see a very high-speed permanent magnet motor of 100,000 RPM. All of these motors, the prototype ones, actually built by our PhD students, so it's part of PhD projects. And each one of these also have the converters, inverters, that means power electronics, and then their controls is also all our students' work. So we are strong in all three areas of a electric drive system, the power electronics, motor, and control. Now coming to the program, so I think you must have received it. It's very small, sorry about that. But the program, first day program, we will be introducing the first part, and then slowly we'll move to the electromagnetism so that we can go to the design part of the motor maybe tomorrow. So we have 3 sections, as you can see today, up to lunchtime today, right? 1 o'clock about. So we'll divide this, now it is about 11 o'clock, so we have 2 hours, 2.5 hours, let's say. So we divide this 2.5 hours into 3 sections. We'll have a bit of break, 5 minutes break maybe, so that you can think what we are talking about. So we'll take a break in each sections. So first of all, I would like you to bring your attention to this figure. So why we are doing transport electrification. The main reason is climate change. Probably all of you are aware of. The temperature is increasing, right? And goal is that we must keep the global temperature increase below 1.5 degrees centigrade. If we go above this, world will be in a tipping point, and there could be no return from there, okay? So we are really in a very serious problem. That's what we should all realize. And why this temperature increase? Perhaps all of you know it's greenhouse gas, carbon dioxide. And carbon dioxide emission, one of the biggest contributors is the energy sector. And under energy sector, 73% comes from energy sector, the carbon emission. And out of that, under energy section, we have energy from industry, that's motor drives in industry. Then we have transportation, next one, which include electric vehicle in the road, boat, ship, train, aerospace, you name it. Everything actually uses a fossil fuel driven engine and contributes carbon dioxide to the environment. So one solution, proposed solution, is that we do electrify the transport so that we can reduce some of these emissions. And that's what is the motivation for electrification of transport. One of very good indication of where world is moving, if we look at the investment trend. Okay, so here in this graph you can see for the last, from 2004 to 2021, how is the where is the money moving, okay, in industry. You can see from about 2017 onward, the green one is the transport electrification, and yellow, big yellow ones is renewable energy. So up to 2017 or 2014 around, it was more renewable energy only, okay? But from 2017 onward, you can start seeing investment moving to the transport electrification as well, okay? And this means there will be a lot of money on R&D and a lot of, as well as a lot of job opportunities for the new researchers and new engineers. So we need to prepare ourselves for that, I guess, and this type of courses are part of it. Now, if we look at the worldwide projected electric vehicles sale, again, you can see by 2040, worldwide, 35% of all new vehicles going to be electric vehicle, okay? And what is this 35% means? It's equivalent to actually 160 billion vehicles sold, okay, new vehicles. And each of these vehicles will, if it's electrified, it will need a motor drive actually. That's what we're going to talk about, right? And 160 million compared to the cars sold worldwide, if we look at like about 400, 500 billions. So 160 billion could look like very small. But I mentioned earlier as well, this sales figure can be compared with what was in 1940, the internal combustion engine sale, okay? And in 100 years, we have now internal combustion engine driven car everywhere, right? Everything is internal combustion engine driven. So in 100 years, it will be same thing. Everything will be electrified, electric vehicle. So that's what we need to be prepared for. And it is also driven by a lot of government policies, as mentioned previously by the director. US wants by 2026 emission to be 160 gram per mile, okay? And European Union wants 130 gram per kilometer emission, carbon emission. And India's long-term goal is to not to exceed per capita emission of developed country, okay? So India hasn't actually set a particular goal. As far as I know, it could be different, it could change, or it might have changed in recent times. Anyone aware of anything? Does India have a goal for carbon emission? Especially for car, vehicle? What is that? 140? G40, 2040 is zero carbon emission, yeah. So 2040, 2050, right? So if zero carbon emission means you have to convert your electric cars to electric, right? There will not be any other way to achieve it, zero carbon emission. Now, you may ask why then, like why it is moving so slow, right? Why electrification of car and vehicles is slow? There are mainly two concerns. One is, of course, cost, right? We can't afford electric car at the moment. It's so expensive. And other is called range anxiety. So range anxiety is not a new thing. Actually, we also have range anxiety when we drive our petrol car, right? You are going on a long drive and your eyes goes to your petrol. How much is there? Is there 2 point, 3 point? How much is left, right? And will you arrive at next petrol pump before running out? So this is the same anxiety you could also have for electric car. Is my battery charge will be enough to take me to my next charging point? And this is so these two are the main concern currently. What prevents the widespread take of electric car, okay? Cost and range. Now range and cost both is contributed also by the battery. So if we look at the cost, especially cost of the powertrain of an electric car, you will see that 55% of the total cost, $55 out of $100 or 55 rupees out of 100 rupees comes from the battery, okay? And rest, 45% comes from the motor, power electronics converter, and controller, okay? So this course, we are not going to talk about battery at all. So we will be concentrating only on that 45%, okay? Because there's a lot of research already on battery and other sources. So we will not talk about battery, but the other 45%, what can be done, okay? And so in the first section, our learning goals, I have make 3 goals for us. So you will be able to describe what is a powertrain, electric powertrain, and then we will be able to classify electric vehicle, and then you will also be able to list desirable performance of electric motor and EV traction drive. And all these goals will be ultimately linked to how the cost and the range we can improve on, okay? So that will be our first section's goal, and then second section will have some other goals and so on. So let's move to first. Let's look at actually the classification first, okay? Let me just make this one a little bit bigger. I go like this. Okay. So we can divide electric vehicles broadly into 3 categories: hybrid electric vehicle, plug-in hybrid electric vehicle, and all-electric vehicle, okay? So hybrid electric vehicle, I believe, already been advertised in Indian market by various companies, right? So it's more or less looks like similar to what you are driving. This is only the powertrain inside is a bit different. You will have a battery, usually a smaller battery, and you still have your engine, you still need your petrol. But the petrol engine could be used to drive the motor, or which will behave like a generator actually. You can produce electricity there and use that electricity to charge the battery. So everything happens inside, so you may not even aware of it. That if this happens, that engine is used to drive the car as well as run a generator to charge battery, and the generator also contributes to drive the car together. We call it hybrid electric vehicle, okay? You don't have to charge the battery outside. You don't have to plug in, and this is the easiest option. So it's already quite popular. Several cars quite popular, even in Indian market it is coming. Then the other one is plug-in hybrid vehicle. So in this case, internal structure is still same, but you could have a plug-in point. So you can charge the battery outside as well. Okay, not just the generator producing electricity and charging the battery, but also you can externally charge the battery. And then the all-electric car, most popular, well-known is the Tesla, Perhaps some of you have seen, heard, or even been advertised in India. Of course, very high-end, very expensive, but that's the electric car which has become the standard kind of Tesla. And in this, you don't have engine. You don't have combustion engine. You don't have any, you don't need any petrol. It is simply battery, a motor. You could have more than one motor, but motor and battery only. So we call it all electric. And this battery you must charge through outside supply. So plug-in. It's a plug-in all electric vehicle. Okay, so we can categorize like this. But in all three cases, the motor, power electronics, control is pretty much same. So whether you do it for hybrid or for or electric, it's same. Only power ratings will be different. High voltage will be different. Voltage level will be different. But basics will be very, very similar. Now let's look at how this power train in the components, the key components, and how it relates. Okay, so most of you drive cars, so you are those who drive car at least familiar with, right? Once you press your accelerator, engine accelerates. So in electric vehicles, the same thing. You press your accelerator pedal, it becomes actually a command. Okay, it could be a speed command or it could be a torque command for a controller. Output of the controllers is going to be a PWM signal for the inverter. Okay, and the inverter is supplied through the battery. So one side is DC and the other side will be your three-phase AC, and that three-phase AC supplies the motor, three-phase motor. And the motor drives your car or drives your wheels. Now, the battery, it could be up to 800 volt. Proposed DC bus is currently 600 volt, but they are talking about bringing it even to high level 800 volt. So why high voltage such as 800 volt? You can charge the battery quicker with high voltage. Okay, so one of the other problem is charging, right? Petrol pump, you go to your petrol pump, you want to fill the tank, it takes how many minutes? 5 minutes? 5 to 10 minutes. But if you want to charge the battery, you need at least, with the fastest charger, 20 minutes. Okay? So, like that's a problem, right? So that therefore, it's a big research area how to improve this charging. What can we do? Okay, and also there is some solutions there, especially for two-wheeler, three-wheelers. The technology calls battery swapping. Maybe I don't know whether it has come to India or not, but battery swapping is that the battery is like a plug-in, plug-out type of thing. So you can take out the battery, put another battery there, fully charged battery. So that will take you a few minutes, which is quite convenient. And it's a big technology. Battery swapping technology is big in China, I understand. Okay, they were even trying to do it in passenger car, even large vehicle like trucks. Okay, for those type of vehicle, charging is a really, really big issue. How quickly you can charge, right? So battery swapping seems to be a good solution there. But the car like Tesla, we can't do it because battery it's under the floor of the car. So you cannot take all the batteries out of it and then put new ones. It's just impossible, okay? So if we want to do battery swapping technology, the architecture of the electric car need to be completely different, okay? So this is the area where India could look at actually, like completely designing their own technology rather than taking what Tesla has proposed, right? That's what China is doing. They try to make their own things. They have made the electric car cheaper. The latest car from China is BYD. It is like they're making it at least 10-15% or up to 20% cheaper than Tesla. So if they can do it, why not us, right? Why not India, right? That's what we need to think about, to think differently out of the square. So that battery, anyway, it could be up to 800 volt, and then you could have a DC-DC converter to reduce it down for the lower voltage that you require for your auxiliary power supply. And you could have a onboard charger. So this picture shows you the key components and how they are linked to the system. So this is what like easily understandable with this picture. At least I find it very easy to understand how electric car works, basically. And I talk about cost. So now let's look at that 45% of the cost, which comes from power electronics and the motors. So this pie chart actually dividing that 45% to, again, under various components. So we have an inverter, we have a DC-DC converter, then we have transmission lines, cables, connections, and a motor. So you may note that the motors and power electronics inverter are actually 60% of the cost. Okay, so if we can reduce cost there, there will be it can like influence the total cost. And so to make it widespread, the electric vehicle, we want it to be cost effective, and cost reduction can happen at motor and power electronics as well as with the battery. But as I said, this course will be only concentrating on motors and power electronics. So for us, there, the cost effectiveness. And we can increase the range by making the motor and power electronics, the whole system, drive system, one, of course, efficient, more efficient, and second, making it lighter and smaller. So how the lighter and smaller can help us? If your powertrain is lighter and smaller, the whole vehicle's weight and size could be smaller. So if it is smaller size and weight, you have better aerodynamics. When the car moves, there is air drag, right? The motor has to overcome that air drag. Now, a lighter and compact car, you can have a better aerodynamics, so that can help you to increase your range, actually. So efficiency and power density, both together, can contribute to improve the range, okay? And making the system smaller and compact also help us to reduce cost, because smaller size, smaller, that means less requirement of critical minerals such as copper, rare earth, magnet material, etc. So that also influences the cost. So usually this becomes the design goals for when you design the drive systems for electric vehicle, these three: efficiency, power density, and cost. This is actually from the US Department of Energy. They have published a set of specification for electric car. It's called Freedom Car 2020 specifications. And according to that, you can see the power is not that high. It's only 30 kilowatt, and maximum peak power is 55 kilowatt. Speed, there are two speeds, you can say rated speed and maximum speed. So we'll talk about it, what this speed means. So rated speed is only 2,800 and maximum could be up to 14,000 RPM. Then if you other components or other parameters, although important, but what I would like you to see is this, the volume and mass. Okay, so volume, they want the volume to be less than 9.7 liter with less than 35 kg. So this relates to our power density. And the speed here, this 2,800 to 40,000, the speed ratio here, you can see, this is known as constant power speed range, or CPSR. So we'll talk about why this is important for EV and why you would like your motor to have wider CPSR when you design for electric car. And of course, we talk about the efficiency. Okay, so these specifications tells us what are the requirements we should have for future electric car. And you may note this torque versus speed characteristic here. So this part, you can note that torque is constant and then torque falls. So when torque falls, this is the basic P is equal to torque times speed from physics, right? Most of you know. So if torque falls when speed increasing, what does it mean? Power can remain constant. Okay? So here, if we draw the power characteristic, so power will increase when torque is constant and speed is increasing. And when torque falls, speed increasing, power will become constant. Okay? So that's why this speed ratio is called constant power speed range. Okay? But we'll talk about why it is important a little bit later. Up to here, let's think what are our key points so far. Or do you have any questions up to here? Yes. 18 seconds. So that is the your acceleration time, it could be, okay? But you can see it is, you need the peak power and peak torque only for very small or short time. So it is, this peak torque and peak power is intermittent rating. It's not continuous rating. You do not need 55 kilowatt for continuously. You only need 55 kilowatt only for 18 seconds, okay, to accelerate, okay? During acceleration, you need the highest power. So you get that, if you get it in 18 seconds, so your power only need to, your motor only need to provide 55 kilowatt only for 18 seconds. So you can put large amount of current without burning the motor, and it is only for 18 seconds, right? So that's the significance of 18 seconds. So how did they come up with 18 seconds? I am not sure, okay? It is, they must have done some kind of research, and 18 seconds found to be the most optimum for acceleration. Probably it gives the drivers a comfort. If you accelerate too fast, that is also sometimes not comfortable for some drivers, right? Only for those who are doing a racing car, for them, they want the thrill to accelerate as quick as possible. But for our drivers like us, we want to accelerate comfortably. So 18 seconds may be coming from that sort of things, okay? Any other questions? Yep. So 325 is the, they are talking about the rated voltage battery, DC bus battery, DC bus of the, your motor scene will see 325 rated and 450 volt. So you could have your line-to-line voltage equal to 415 volt for the motor. Okay, because when you do the inverter with a two-level, three-phase inverter. Yes, sorry, where is that This is the one you are talking about, right? So battery voltage could be higher, okay, because you could have a DC-DC boost converter as well, or you could, buck converter. You can reduce it, the voltage seen by the motor, you can reduce it. But you could, battery voltage could be higher, like up to 800 volt they are proposing. So why 800 volt? As I mentioned, it could help you to do the charging fast, because you can. I don't exactly know how much it was allowed, but I believe if you talk about a ripple, right? Fluctuation is basically ripple in your DC bus voltage. So it's not more than 5 to 10%. You should not allow more than 5 to 10% in the DC bus fluctuation. Yes. So that for what motor sees, okay, this specification is actually for a motor design purpose, okay. This 2020 Freedom Car specification, when they provided, they wanted the traction motor to achieve all this, okay. For that purpose, the motor should see at least that range, okay. Not too low, not lower than 200, or not higher than 450, so within that range. But battery voltage could be higher, okay. And there is a reason why you want to keep the voltage low for permanent magnet motor, is that if your controller fails and motor is speeding, it will have induced voltage, uncontrolled induced voltage. So if that voltage is higher than what battery can withstand, then it can burn the whole system, okay? So that's why you want the motor voltage to be relatively lower. You don't want a motor with 800 volt, okay? Because if you have 800 volt and you can't control it and it's spinning at a very high speed, it can exceed 800 volt and it can burn the system, okay? Anything else? So let's think about the key points so far together. What's the key point so far? Sorry? Types of EVs. Okay. Good. Let's try to recall, right? Otherwise, we sit here and after some time we'll forget what we have talked about. So let's try to write it down. Okay, types of EV we have talked about. Anything else? Key components of EV, right? EV traction drive. Cost and range, right? Cost and range challenges. Yes. So remember this when we move to the next part, right? Okay, so let's move to the next one. So next part, we'll be talking about the fundamentals of the traction drive. And you should be able to now understand why CPSR, constant power speed range, is important. And of course, why also high power density and efficiency important. And how to calculate power required by a traction motor from very fundamental equations. And we will list some of the key challenges, okay? So this is what we'll try to do in the next half. It may not be 60 minutes, okay? I think we did it. If we can finish earlier. So let's try to understand the CPSR first. All of those who drive car, you know when you start with first gear, right? And then once it accelerates, you change to second gear, third gear, and so on as you increase your speed. So when we do that, what the internal combustion engine does is gives us a torque versus speed characteristic is somewhat like this, shown here, okay? you have somewhat about a constant torque when you are in first gear, when you are accelerating. And as you go from there to the next speed and so on, change gear, you get your torque requirements or the force requirements start to reduce, okay? So this is, we get this type of torque speed characteristic in a internal combustion engine forcefully. The internal combustion engine's characteristic is not like this. We achieve it through those gears, okay? But in an electric motor, we can design the motor like this, having a torque speed characteristic, a constant torque and reduce as the speed increase. We can design it like that, okay? So that's the biggest advantage of a actually electric motor compared to a combustion engine, okay? We can get this natural characteristic required by traction drive out of the motor very easily. And so now when we talk about that constant power speed range, which I already mentioned a little bit, that when torque falls, speed increase, we can have this constant power, okay? So how, up to what speed you want to keep this power constant? What's the significance of it? What is this base speed or rated speed, and what is this maximum speed, okay? And what is, and how, why it is significant. So let's define our constant power speed ratio or range as the ratio of the maximum speed over base speed, okay? It could be rotational speed of the motor, or it could be your linear speed of the vehicle. Either way we can define it. And so here you can see the force versus speed, same characteristic. The previous one was torque versus rotational speed. This one is the same characteristic, but force versus linear speed, okay? Again, this is your minimum speed up to which you accelerate in your first gear. And this is your, let's say, second gear. We can also go up to here, but just to keep it simple, let's keep it to the second gear speed, okay? So we call it the ratio of the minimum speed, VRM, this is linear speed, okay? About 30 mile per hour. And let's say the second gear, it goes to 60 mile per hour. So the ratio of those two is 60 to 30 is about 2, right? So that's the ratio here. Now, to understand its significance, let's start with a very basic equation. We all know force is mass time acceleration, right? From Newton's law. So from there, the force over mass m can be acceleration, dv dt. And if we just rearrange it, and we will be able to actually calculate out how much acceleration time if we integrate it, right? Mass integrating from 0 to the maximum speed of the second gear, dv over f, and time required to accelerate 0 to tf integrating dt, okay? But in this range from 0 to W max or 0 to VRV, we can divide our integration, or we can separate our integration into two components. One from 0 to the minimum speed here, and from minimum speed to the maximum speed under second gear. Okay, so we do this integration, and we can replace the force F in terms of power over speed, right? We can, force time speed is your power, so we can replace force here by power over speed, okay? Why we want to do that? Because we want to see how the CPSR affects power, because that's the importance, okay? So we are writing this in terms of power instead of force. So after we do this integration, a bit of maths, you will get the expression of power required in terms of mass, total mass of your vehicle, acceleration time, and the two velocities, the minimum velocity to accelerate and the maximum velocity in one gear, okay? So in this equation now, we can write this equation in terms of CPSR now, okay? We have defined CPSR as omega b over omega max, or we can, sorry, omega max over omega b, or we can define it as VRV if we do the linear velocity, and VRM. We could also define like this, it's the same thing, okay? So now we're going to write this equation, the power equation, in terms of CPSR. In the next slide. So if we do that, and we could write it also in terms of rotational speed. So if we write it in terms of rotational speed and rotational speed, then this mass becomes our inertia, okay? Mass time square of the radius. Radius here will be the radius of the wheel, okay, of your car. So if we write it in terms of rotational speed, it becomes inertia over 2 times acceleration time square of the maximum and minimum speed, okay? And if we now consider this CPSR, that's what we have defined previously, which could also be, we can consider as omega Rm over omega Rv, or Vrm over Vrv, same thing. Let's say the CPSR, if your base speed is, let's say, 0, okay? If your base speed is 0, then your CPSR is infinite, right? Your constant power speed range is infinite. What does this infinite CPSR mean is that you will have constant power from 0 speed to the maximum speed. Or torque will be maximum torque at 0 speed, and torque will start to fall. Okay, so you will have a characteristic torque versus speed characteristic like this, right? And if I now use that my base speed is 0, that means omega Rm is 0, my equation, this power equation will becomes half inertia maximum speed squared over the acceleration time, right? This is our best scenario we could have. However, it's just not practical. No motor can have constant power from 0 speed to the maximum speed, okay? The second condition could be that we have no maximum speed, or our maximum speed and base speed or rated speed is the same speed, okay, equal. So if they're equal, then our CPSR is 1, okay? If these two speeds are equal, then our power equation becomes inertia over maximum speed squared over TF. Compare this and this power requirement. Immediately you can see if you have infinite CPSR, power requirement would have been half the power required by when there is no CPSR, okay? But obviously we cannot reduce the power to half because we cannot have infinite CPSR. Practically it's not possible. But if you have large CPSR, that means power requirement may not be 50%, but it could be 70%, 60%, 80% of the power that you will need if there's no CPSR, okay? So that's the meaning of this. And because of that, you want for traction motor to have wide CPSR, wide constant power speed range, okay? How do we get constant power speed range in a permanent magnet motor? That's a different story, which we'll talk later when we'll talk about control, okay? But this is why you want constant power speed range, okay? Wider constant power speed range. And in our 2020 Freedom Car specification, the speed they have proposed 2800 as their base speed and 14,000 as their maximum speed. So ratio is about 5, right? So they are saying CPSR of 5 will be a good CPSR for a traction motor drive. Okay, you cannot get it finite, but about 5. Okay, is a good point, good starting point. So that's the CPSR. The next, let's look at what's happening in the current, what is the current trend in terms of density, making the motor lighter or making the powertrain, electric powertrain, lighter and compact. Okay, let's see what's happening there. So if we consider just a motor, a conventional induction motor or a DC motor, the power density is actually very poor. Okay, they are because these motors, when they have designed conventionally, we have never ever optimized them to reduce weight or reduce mass. Our goal was to increase efficiency maybe, or just to get whatever torque we want. We hardly care about material that we are wasting, right? The copper, the electrical steel, everything, we have wasted a lot, and we hardly cared about making them lighter or smaller. But in case of electric car, remember you have very limited space, right? You are replacing this where you have your internal combustion engine. You are replacing that with a motor and a power electronics converter. So you have very, very limited space. So you have to have certain size, okay? And that actually has forced designers to look at the power density, okay? We can define the power density two ways. One is the volume, that means the size, the power versus power over volume, that is kilowatt over liter or kilowatt over meter cube. And other one is known more as specific power density, which is kilowatt over kg, okay? So specific power density is very, very important actually for electric aircraft, because for electric aircraft, rather than size, weight is much more important, right? So for electric aircraft, when they design motor, the biggest goal is how to make it lighter. That means kilowatt per kg, how to make it as large as possible. Whereas for EV, both like the volume is more important than the weight, but actually if we can get better in both, will improve a lot of things. So they have tried, especially the commercial vehicle manufacturers. The highest kilowatt per liter achieved by Model 3, this is Tesla Model 3, about 40, less than 40, between 35 and 40, so about 40 kilowatt per liter. And also by Chevy Volt, these two motors have achieved the highest power density so far. Using, both of them actually use permanent magnet motors. And in terms, these are the all electric vehicles, okay, the first group. The second group is hybrid electric vehicle. So for hybrid electric vehicle, BMW has achieved the highest with again close to 35. Okay, so for hybrid vehicle, you can see power density is less, okay, compared to full electric vehicle. It's 35 and 40 maximum achieved. And the specific power density, that is kilowatt per kg, this one, highest was achieved by Tesla, that is about 4.5. A conventional motor, it is not even 1. Okay, in a conventional motor, it is 0.5 kilowatt per kg. Okay, maybe those who have seen a 500 watts motor, many of your labs have 500 watts motors, right? Induction motor or DC motor or conventional motors. They are definitely weight more than a kg, right? So that means for conventional motors, it's not even 0.5 kilowatt per kg, right? And look at what has been achieved in the electric vehicle, 4 kilowatt per kg. So a motor of 4 kilowatt weighs only a kg, okay? So same thing for the, I think for hybrid electric, it was achieved by Sevi volt, okay, but less, about 3.5 kilowatt per kg. And it has been actually continuously improving. If you see here, the year from 2004 to 2018, this is the kilowatt per kg for different automotive companies, how they are improving it. This is for hybrid cars, so it's about it started about 1. Toyota Prius, the PM motor, which is considered as a base mark for traction motor, so they started with about 1 kilowatt per kg and have improved by 2018 to close to 2 kilowatt per kg. Okay, and these BMW, I think they have achieved about 3.5 by 2018, but they're still improving it. Okay, so we have data here only up to 2018. So how did they achieve that? We'll look into it. Okay, it's a challenge. How do you make a motor so light, or how do you make a motor so small? Okay, so that's one of the challenge. And so if we look at the overall, the motor plus power electronics together, because it's not just a motor, you also have the power electronics together, which gives you the actual power density for the whole powertrain, right? So this is data for 2010 to 2020. Motor, you can see the kilowatt per liter improvement and kilowatt per kg improvement and cost reduction, okay, for the motor alone here. And this is for the inverter, okay, same thing, you can see improvement in cost, improvement in power density, okay, and together overall improvement in the last 10 years, okay? And of course the efficiency, okay? Efficiency is also improving. The challenge, as I said, is high power density means you have a very small motor, means you need intensive cooling. So when you have to consider cooling while designing the motor, that means your motor is no longer an electromagnetic problem, it becomes also a thermal problem. So it becomes a multi-physics problem, okay? You may have to also look at mechanical stress. So if we consider mechanical, thermal, and electromagnetic together while designing the motor or power electronics even, it becomes actually a multi-physics problem. Okay, and you want to optimize, or you want to, let's say, maximize the densities, maximize the efficiency. So that becomes your goal, right? Your objective. So it becomes a multi-objective problem, okay? So motor designs is no longer simply a design problem. It's a multi-physics, multi-objective problem, okay? Let's look at also the case of efficiency, okay? So here in the previous slide, you have seen the efficiency, okay, 95% efficiency, greater than 95% efficiency. It's okay for laymen to say a motor efficiency is 95%. But those who are expert, actually 95% doesn't mean anything, because efficiency for motor is not a single point, it's a map, okay? Efficiency of a motor is actually a map, okay? You have to look at the efficiency, torque versus speed, various torque, various speed. And you can get many different efficiency for different operating conditions, okay? So when they say 95% efficiency, they mean that it's only here for an example motor case, let's say traction motor case, okay? And this is 95% efficiency is only when you are driving the car in the city driving. That means, let's say 50 kilometer per hour, 40 to 50 kilometer per hour speed, stopping in various red light if you have traffic lights or traffic, okay? So city driving, you get that highest efficiency. But for the same motor, while starting and accelerating, the efficiency could be as low as 80%, 85%, okay? Similarly, while you are driving the highway, 100 kilometer per hour, again, your efficiency could be as low as 85%, 90%, okay? So in the extreme end, efficiency is no longer 95%. And so some solution, like for example, Tesla is trying to have different motors for this different operating condition. They will have a motor for acceleration. They will have a motor for city driving. So you will have more than one motor in the car, okay? One for highway driving. So they optimize that motor, which is used for highway driving, to have highest efficiency here, okay? Or the motor they are using for starting could have the highest efficiency here, okay? But if you want to have more than one motor, remember, we have space constraint. The car, we don't have unlimited space. We have just limited space. So putting 3 heavy motors is not a solution again, right? So that's another thing which we should, research area which we should think about. As efficiency, even though we have achieved 95%, maybe we can push the efficiency only another 4%, let's say 99% maximum efficiency you can get. No more than that, right? Just not possible. Physics will not allow us. So, but this is only, even though it's only 2 to 4% increase, but it could be a big effect on many other things, okay? So never think that, okay, we have only 2% efficiency increase. What does that mean? But that 2% efficiency could have a bigger impact on the whole system. But optimizing efficiency is a big, again, it's not straightforward because it's all linked, right? So we could have where does this efficiency is related to losses, right? So you could, the 3 main losses. One is your copper loss in the wires, iron loss in the magnetic core, and the mechanical loss, right? 3 losses. So usually when high torque, you need high current. So during the acceleration, your copper loss is highest. And in the highway driving, when you are driving at high speed, your iron loss or core loss is highest, okay? And so if I want to reduce core loss, I have to reduce core loss or iron loss is function of frequency, and frequency means speed, and the magnetic flux. Okay? So if I want to reduce iron loss, I have to either reduce my speed or I have to reduce my flux. But if I reduce magnetic flux, I will also reduce my torque and power, right? Same thing, if I want to reduce copper loss is I square R, so I will either reduce my current or I will reduce my resistance, right? So if I reduce current, again, I will affect my torque, right, and power. And if I want to reduce resistance, maybe there will be your wire size will be affected, right? R resistance is coming from the length and your cross-sectional area of the copper wire. So that is also may not be feasible. In other words, they are all interlinked. Okay, efficiency improvement is all interlinked. So again, it becomes actually optimization problem. There is a trade-off. You have to trade off between your torque, power, and losses. Okay, so it's again an optimization problem. And efficiency optimization is mostly could be treated as an electromagnetic problem if we don't consider thermal, but for more aggressive design, it could become a multi-physics problem, because the thermal will come, okay? If you put more current in a smaller area, it becomes a thermal problem, okay? How to dissipate the heat effectively. So the next part is we spent about an hour. That's okay, right? Yeah. Okay, so now let's look at what type of motors are being used. When we talk about, although this course is about PM motor, but let's see what other type of motors are being used and how they compare in terms of power density, efficiency, etc. And again, you can see some of the most recent proposed motors in the commercial vehicles. OD has proposed in 2025 to use induction motor, okay, induction motor. And BMW has proposed to use current excited conventional synchronous motor. Other than those two, all are PMSM, permanent magnet synchronous motor, okay? Kia, Tesla Model Y, Model S, Model 3, Lucid. Lucid is one of the most recent, and this Lucid is, they have achieved in one battery charge 600 kilometer, okay? So, but how did they do it? Just putting bigger batteries, actually, no, and making the motor a little bit better. Not some very innovative something, okay? But they claim to have the highest or longest range with one battery charge. They have 3 motors, you can see. Their voltage is 924 DC battery voltage, okay? As I said, 800 volt, so they're even pushing for 901 kV volt. If we compare the very basic of these 3 motors, that's induction motor, permanent magnet synchronous motor, and conventional synchronous motor, stator is exactly same for all 3 motors. I can use a stator of an induction motor, just replace the rotor with a permanent magnet or with a synchronous motors rotor, okay? Induction motor, you will have copper bars or aluminum bar in the rotor, case induction motor. In case of conventional synchronous motor, you will have DC winding in the rotor, DC excitation winding. And in permanent magnet, you will have permanent magnets, okay? So the innovation is mostly in the rotor, actually, okay? Because stator is more or less same. And if we compare these motors, the power density, what we talk about, that kilowatt per kg especially, you may note that the highest kilowatt per kg was achieved actually in an axial flux type permanent magnet motor. 8 kilowatt per kg, okay? No one can compete with it. No other motor can compete with them, okay? But the axial flux permanent magnet motor has its own problems, okay? That's why they are not as popular as the other permanent magnet motors. PMSM here, about 3 kilowatt per kg on average. Synchronous reluctance motor, permanent magnet, assisted reluctance motor, AC induction motor. So all these are below PMSM. Okay, so power density wise, PMSM or axial flux PM motor comes out as the best. Okay, and then if we look at the other things, cost, maturity, technical maturity, torque density, power factor, efficiency, etc., you will note that not that PMSM always comes out as first, okay? Some other motors are also good. For example, let's say torque density. So torque density, green one and the blue one. Green one is actually synchronous reluctance motor. Blue one is conventional synchronous motor. Okay, WRSM means rotor excited synchronous motor. Okay. But if we look at the technical maturity, again in the technical maturity, we'll see that axial flux motor, even though it has highest power density, it does not have the technical maturity yet. Okay, that's why one of the reasons why it is not yet popular. Okay, its manufacturing is a big problem. Okay, it's not easy to manufacture, so because of that, its cost is also very high. Okay, axial flux motor. So overall, PMSM come as the best choice, and that's why you see in the many automotive companies goes for PMSM as their traction motor. Okay. Same thing, you can look at the efficiency. So induction motor, conventional induction motor, actually good. You can get the highest efficiency point for high speed. Okay, but they are not very good at high torque region. Okay, and the synchronous motor, conventional synchronous motor, again, they are not very good for high speed part. Whereas PMSM relatively can cover both the high torque region and the high speed region. So that's another reason why they are popular. Okay, PMSM. So this is basically summarizing what we are talking about. PM machine has higher efficiency as well as high power density. Why they have high efficiency? Because their rotors, they don't have any windings, right? Their rotor only have magnets, and magnets theoretically doesn't have any losses. So you save the rotor losses. That's why PM motor, they have higher efficiency compared to the conventional one. And the magnet also have very high power, high energy density. The magnet, rare earth magnet, which allow them to have smaller size. So compared to a conventional induction or synchronous motor, there could be up to 35% reduction in the size for a PMSM. Okay? But there is always a but. So cost. They have the cost-wise, PMSM is costly because the rare earth material, we'll talk about them later, but they are the most expensive component in the motor, the rare earth materials. And of course, the inverter is as well one of the costly part, okay? And PMSM you cannot run without the converter, even if it's not with EV, outside also. If you want to use a PMSM motor for other purpose, let's say running a fan or running a pump, you will still need a power electronics converter. It's not a like a online start. It cannot start just by plugging in three-phase supply like an induction or synchronous motor. Okay, so it has that issue. But why it required that, we will talk about maybe when we discuss the controls. And another one, which is it's a trend. I said that in stator there is not much innovation. The only innovation is a new type of windings being used called hairpin winding. And this hairpin winding, the advantage of hairpin winding is that you can do direct cooling. Okay, the winding can be cooled directly by pushing coolant. Just like this could be like a kind of like a pipe, the windings, and you can make coolant pass through them. So you could have direct cooling. And direct cooling means you can push much larger amount of current through them compared to the conventional copper wire. And another trend is this increasing speed. Okay, base speed and the maximum speed is increasing. So for Toyota Prius, as we talk about, when they started in 2002, their maximum speed was only 6,000 RPM. But by 2017, that speed has gone to 17,000 RPM. Okay, nearly 3 times increase. Same, and this is because with increasing speed, they can improve that kilowatt per kg. Okay, 1.2 kilowatt per kg to 1.7 kilowatt per kg. They have achieved just by increasing the speed. And you can see how the size reduction has happened as the speed increase in various years for Toyota Prius. For the Tesla and Lucid, the speed is even higher, 90,000 RPM. Okay, and so they have achieved actually higher than the 2020 Freedom Car specification. Freedom Car specification said 14,000 is sufficient, but they have achieved even higher than that. Okay. Now the challenges. So to increase CPSR, we talk about CPSR and we said higher CPSR is better. So it will allow us to use a lower power rated motor. So compact size, lightweight, we can achieve. But to get constant power speed range, you will need to have much more complex control. Okay, especially if it's a PM motor. So control becomes complex. It must have flux weakening capability. So flux weakening capability means when it goes to high speed, you want to reduce the flux. Now in a magnet, reduction of flux appears like, how can you reduce the flux of a magnet, right? So that means it actually achieved through control. So we'll talk about that later. But that flux weakening capability will be required whatever motor you use. In induction motor, it's possible, but this flux weakening range is no more than 2. Okay, so ratio is only 2, whereas we want 5 or more. Okay, in synchronous motor, you can achieve it, but you must have a complex field current control. Usually conventional synchronous motor, we don't do the field control much, right? but you have to have, so that's a research area actually people are looking at, whether we can use synchronous motor and do complex field control to get this flux weakening and avoid using rare earth magnet motors. Okay. Other one was the increasing speed. This increasing speed, again, it can give us the high power density, but high speed means you will have high iron loss or core loss, since it is the function of frequency squared. So frequency is your speed. So high speed means high core loss, high mechanical loss. Friction loss is proportional to speed. And you will need intensive cooling. You will need to consider the mechanical strength of the rotor as well when it's spin at a high speed. Okay, so these are the challenges when you design the motor for high speed. And increasing CPSR has the control problems, could have control problem, and you must consider also demagnetization risk, because you are reducing the flux by using armature reaction, actually, DC motors armature reaction. So you're applying a negative flux to reduce the total flux. So that negative flux, if it's too high, it can actually permanently demagnetize your magnet. So you must consider that while designing, while considering CPSR in the traction motor design. And this is, I already talked about, the hairpin winding for direct cooling. Okay, so should we take a break? Right? Maybe everyone wants to take a break, yeah? And then maybe another 20, 30 minutes, we can finish. Okay? Yeah, if you want to take a, go to washroom, anything, so please feel free. We'll take 5 minutes break, right? motor side, and when we do that, we will multiply the motor and load torque by the square of the gear ratio, and the damping or coefficient also by square of the gear ratio, and load torque we multiply it by the gear ratio, okay, not square. Remember that torque is not multiplied by square, it is only the gear ratio. So same equation can also be used for geared system after referring the quantities. And in this we will be interested to calculate actually this Tm, that motor torque, as well as the power related to it in a electric traction system. And the load torque, TL, is your actually tractive force demanded by the wheel. Okay, so if we know TL, and we can estimate inertia and also damping coefficient roughly, so we will be able to calculate out the motor, the torque demanded from the motor and power demanded from the motor. So this is what we will try to do, okay, in the next slides. Now, what are the forces that the motor has to overcome? First of all, you have to overcome the gravitational force, right? That is mass. So let's consider the worst case. When a car moves on a slope, it requires the highest amount of force, right? So let's say the road has a slope of an angle beta. So then the force, the gravitational force is mass times gravitational constant g times sine of that slope angle, sine beta, is the force, gravitational force need to be overcome by the motor, first force. The second one is the force on the friction force of the wheel. When the wheel moves on the road, it has to overcome the friction of the wheel tire on the road. So that force is also in fact related to your gravitational force, but it's cosine component, okay? mg cos beta. So this force, this rolling, is sometimes referred as rolling resistance force. This force is in fact is always present whether you have the slope or not, okay? If your slope angle is 0, this becomes mg. If you have slope angle 0, then in fact this gravitational force mg sine beta becomes 0, okay? So if you have slope, that you have an additional force, mg sine beta. If you don't have a slope in your road, then this force, gravitational force, becomes 0. Sine component becomes 0. But cosine component is always present, and usually it's multiplied by how rough your road is, okay, by a coefficient known as rolling friction coefficient. And this coefficient is empirically determined, so you can find out what is this value for a rough surface or for pitch road or for concrete road or whatever, okay? So this value will be different, usually less than 1, 0.4 to 0.35 to 0.4, about that. You can find, actually, if you look for it, possibly even for Indian roads, you may find this information, what is the rolling coefficient for Indian pitch road. For, I think, US or even for some Australia, it's like 0.35 something. So for India, it will be similar, maybe slightly different, but you can find that value, okay? And then third one is the aerodynamic drag. When the car moves, car has to overcome the air force from the air, right? Air friction, basically. Okay, so this, which is known as aerodynamic drag force, and it's calculated from the density of the air, half time density of the air, multiplied by the cross-sectional area of the front of your wheel, AF, times the square of the velocity, times a coefficient or constant known as aerodynamic drag coefficient, CD. And this CD is, again, could be different for different vehicle because it depends on the design of the vehicle actually. For example, here at the bottom you can see there is a kind of like Jeep type of vehicle where the front area is much larger. So this coefficient CD is about 0.5, whereas for a passenger car where your front area is relatively smaller or narrower, it is 0.3. Okay, and so it could be different for different type of vehicles. And so this force, this aerodynamic force, we should also remember that this, if we multiply this force by velocity, we get the power, right? So power related to aerodynamic force or aerodynamic drag force is, if we multiply this force by velocity, the power becomes actually function of cube of the velocity. Okay, so higher the speed of your car, higher will be this dragging force. Okay, and you can calculate out for the worst case scenario, the highest speed, what will be this force. Okay, so we can calculate all these three forces, and together, if we sum it up, we will actually get the your total force, which is actually your load related to load torque or load force. Okay, that in our previous slide, the TL. So TL relate to this force actually. If we multiply the force by radius of the wheel, it will become torque. Okay, and the if we ignore the damping coefficient, usually D is very, very small. In our previous torque equation, D times omega. So if we assume there is very little viscous friction, D is very small. So if we ignore D omega m term, then in terms of force instead of torque, the difference between the motor's tractive force required from the motor minus all this force that we have to overcome is equal to your acceleration force. Okay, if the car is not accelerating but just running it steady state, then this term becomes, this accelerative term becomes 0. Okay, at steady state this is 0. So at steady state, tractive force is equal to the force required by the tractive force of the motor equal to the force that it needs to overcome, which is the rolling resistance, air drag, and the gravitational force if there is a slope. Okay, so we can calculate out from there what is the force required from the motor. And if we multiply the force by the radius of the wheel, we'll get the torque. Okay, so very easily it can be calculated. And usually, when we express it in the terms of force and linear velocity, this mass is multiplied by a factor higher than 1, known as sometimes it's called the rotational inertia coefficient. This, in fact, just account for mass of the motor or the mass that is present in the additional mass that is present in the car, like passengers, let's say, or weight or something. Okay, so this factor increases the total mass of the car body. And this equation, that when we convert this to torque by multiplying by the radius, which is the wheel radius, we will immediately know what is the torque required by the motor. And this equation we can compare kind of a very basic equation of, let's say, the pulley system. Okay, in pulley system, remember a motor is in the rotational, has the rotational motion, and a mass moves linearly, right? Going up and down. Car, it is actually same thing. The motor rotates, but the car moves linearly, right? It's not going up and down, but it's going horizontally, moving at a certain velocity. So using that concept of this pulley drive system, we can calculate out also the equivalent inertia of the rotating mass in the motor system. Okay, you can compare these two equations here, and this linear mass moving up is equivalent to a equivalent inertia, the mass time r squared. Okay, similarly here, so that means the total inertia is not just the inertia of the motor, but this m times r squared. So that means the inertia is slightly higher. So that's the factor which is accounted by this km in our equation. Okay, this is the equivalent linear mass, equivalent inertia when you convert it. So we could calculate torque, and we can also calculate power directly from there. So this is the starting point. Actually, if you are doing a traction design, this will be your starting point. Okay, calculate the torque and power from this basic equation, and then from there onward you do all rest of the things. Okay. This is an example. I think we'll share the slides later, right? So you can look at this slide. This is a numerical problem, a very simple numerical problem, which shows how you can calculate this power from for a car moving with a slope. Okay, how these forces are calculated numerically using those equations just we talk about. Okay, I can give you a few minutes to have a look because it's just maths. I don't need to read out. You can look for yourself. Okay. This is a small car. As you can see, it only needs 20, how much kilowatt? 29 kilowatt. Okay, it's relatively small motor using a 42-volt battery. So it's just kind of a small system. Okay, but you can use the same process to calculate the power of any other car. Okay. We have taken the break. We have so we'll move forward. So this is the last part of today's. I think we'll take maybe 20 minutes. Will be okay, right? Okay, we'll try to do this in 20-30 minutes. So rest part is actually refresher on electromagnetic. As we said, we can probably move quite fast because this is most of you should be familiar with. It's more about recalling certain things so that we are ready tomorrow's actual design problems. Okay, so that's why we will be doing this part. In case someone hasn't done electromagnetism before, this will help them as well. So this next part, the goal is to recall some of the fundamentals of electromagnetism, trying to see whether how the magnetic circuit can be used to do analytical calculation of a motor. And also we will try to identify what are the limitations. Why cannot we simply use magnetic circuit to design motors? Why we need those sophisticated finite element analysis, okay? All are familiar with B and H? right? Is there anyone who doesn't recall B and H? Okay, so B is the flux density, H is the flux intensity. And the relation is B is equal to mu H. Mu is called permeability, and permeability is equal to permeability of air or vacuum, mu naught, which is a constant, and mu r is the relative permeability. Okay, so if we simply look at this equation, we may think that B and H is linear, but it's not for electrical steel. Okay, there is a nonlinearity. The next one is flux. We should remember the B flux density, if you multiply it by the cross-sectional area through which the flux is passing, gives you the flux. And flux, we can also actually, it's actually the definition of flux is coming from the your first postulate of magnetic field, that is the div or diversion of flux B is 0, if someone recalls. What does that physically mean is that a piece of magnet, if you cut it, you can never separate north and south pole, right? North and south pole always exist together. Even if you cut it, a new north and south pole will appear there. Okay, so that is mathematically becomes that magnetic flux or magnetic flux density. It doesn't divert away. It's only which is the mathematical form is div of B is 0. Okay, that's the differential form of the to express that. And that also leads us to that in a closed total flux in a magnetic circuit must be always 0, like the current, right? Kirchhoff's current law. Similarly, we have this first postulate is actually kind of Kirchhoff's law of the magnetic flux. Total flux in the magnetic circuit always must be 0. And the other important component is magnetic vector potential, and this comes very much from the your relation vector relation of the first postulate, that is div of B is 0. So according to vector calculus, if div of a vector is 0, then that same vector can also be expressed as a curl of another vector. Okay, so that another vector in case of magnetic field is here, as you can see, this A. This A is known as vector magnetic potential. And you should remember, that magnetic vector potential is not unlike the electric potential. Electric potential you can measure, which is your voltage, right? But magnetic potential we cannot measure. It's actually a mathematical term. It's not physically, it doesn't physically exist, okay? But it helps us actually to solve magnetic density and develop a equation, differential equation, to do the calculations such as finite element analysis, okay? So B, the flux density, is that means can be expressed as a curl of the magnetic vector potential. And we can, if we know magnetic vector potential, we can directly find also flux. So flux is kind of like current, and magnetic potential is kind of like voltage for magnetic circuits. And another thing is that using the magnetic vector potential, we can find a second order differential equation known as vector Poisson's equation. So that this is Laplacian, this del square is known as Laplacians. Laplacians of magnetic vector is equal to permeability times current density, negative of permeability, because this is again coming from fundamental magnetics, electromagnetics. And this is actually a second order differential equation, okay? In fact, all the finite element analysis that we talk about, they try to solve this equation at the back, okay, which we don't see in those who use finite elements. You only see the geometry and you just see how they have solved the flux density, etc. But in the back side, actually, it is trying to solve this equation. Okay, it could be a three-dimensional equation. A could be function of x, y, z. So it's a three-dimensional second-order differential equation. And you have to solve it using numerical methods such as finite element. Okay. And then the other equations are Maxwell's equations. Okay, that the four Maxwell's equations. First one is actually related to electrostatic. Second one is magnetics. Third one is also magnetics. And the last one actually relates electrostatic with the magnetics to give us electromagnetics. Okay. And these four equations again are the base of many finite element analysis. Okay. Together with Poisson's equation, that's what they solve. Okay, finite element and software packages, these are the equations they solve. We may discuss a bit more later, but just today we are reminding you that these basic equations. And then this is basically telling you or reminding us why the electrical steel has non-linear characteristic. Okay, if we simply look at B equal to mu H, it appears like mu is a constant, so B equal to mu H should have been linear. Why in electric steel we have this non-linear part? So it comes from the saturation, right? Magnetic saturation. What does the magnetic saturation means? We'll refer to them a lot later. So what does magnetic saturation actually means is that in the, let's say the case of iron or electric steel, you have dipoles, magnetic dipoles. And these magnetic dipoles are one region of the material, the magnetic dipoles are aligned in a particular direction, okay? But this direction are usually random. So there is no net magnetic dipoles. But if you magnetize it, electrical steel, all the dipoles align into one direction. And when they are all aligned, then we say it is saturated. The material is magnetically saturated. And even if we keep increasing H when they are saturated, we do not get any more higher magnetic flux density. Okay, so that's the saturation. And usually we can use Ampere's law, basic Ampere's law, to calculate flux using magnetic circuit. In fact, magnetic circuit is coming from this Ampere's law. Okay, and so the basic law is line integral of H, closed line integral of H is equal to number of turns times current. So if we consider this very simple magnetic circuit, we have a ring, iron ring, and let's say we have a coil here, and current is passing through this coil. So, and it has n number of turns in this coil. And when the current passes through this coil, it is going to induce magnetic flux. And this magnetic flux, if this ring is iron ring, then the flux should be flowing in this ring. Okay? So this circuit we can write taking help of Ampere's law. So line integral of H times L. So L is in this case this closed path. closed flux path. So it's a circle, in our case 2 pi r simply. Okay, if the radius, mean radius of this ring is r, then LC, or length, core length, is 2 pi r simply, equal to number of turns time current. So this Ni is known as MMF, magnetomotive force, which forces the flux to pass through. And from there we can, if we express this in terms of flux, then flux becomes equal to mu Ni S. S is the cross-sectional area of the ring, Lc is the length, and mu is the permeability. So this, in this expression, S over Lc time mu, this part, can be, it's kind of like a resistance. If you recall, a resistance of a coil, a resistance of a wire is length over surface area times the resistivity, right? In case of magnetic circuit, it is again length over cross-sectional area, but times over permeability, mu. And this component is called reluctance, okay? So the ring that we have here, we can write it like a circuit, or we can draw like a circuit. So in this circuit, this reluctance is like our resistance. Ni is like your voltage, which is the MMF in case of magnetic circuit. And what is flowing through it is the flux. So any magnetic device, including motor, in fact, we can use this reluctance MMF and can draw like a circuit and can calculate flux analytically, okay, and which is known as magnetic equivalent circuit. Can you see any issue? What is the limitation of this type of problem? Like, why we cannot always use magnetic circuit? What's the problem? To calculate reluctance, what's the problem? Why cannot we calculate reluctance always for everything, every magnetic devices? To calculate reluctance, I need to know the length of the close length of the flux path, LC. I need to know the cross-sectional area, S, and I need to know the permeability. So let's say I have a motor. I know the geometry, so I know what is cross-sectional area. I know LC, but I may not know accurately permeability, okay? Because your permeability is not constant. When it is saturating, permeability is no longer constant, right? Permeability constant only here in the linear region. So if mu may not be, you may not be able to estimate mu accurately, because the most of the time motors will have magnetic saturation, okay? So that's why if we use magnetic circuit to find flux in a motor, it will always overestimate because it ignores saturation, okay? And the other problem is the leakage and the fringing. So in the motor, we always have an air gap between the stator and rotor. So when you have air gap, some flux may not cross the air gap, which is the leakage flux. Again, the estimation of leakage flux linearly is difficult. And also in the air gap, when we use Ampere's law, we assume that flux is perpendicular to the cross-sectional area through which it is passing. But in reality, they may not at the edge of the gap. They could have fringing. So fringing means, again, the estimation may not be correct, okay? So in magnetic circuit, equivalent magnetic circuit method, you ignore fringing, you ignore leakage, you even ignore saturation. That's why this method, it may not give you accurate flux information, and almost always overestimate it, okay? This is just some magnetic solutions. This is just, I will skip this. You can look at it with the slides later. So here is a motor equivalence, magnetic equivalent circuit, how you can draw them. It's not that you can't, you can draw it. So in your left-hand side, you can see a surface type permanent magnet motor. In your right-hand side, you are seeing a interior type permanent magnet motor. And here they are attempting to draw the equivalent circuit by drawing the reluctance, okay, various reluctance of various parts, okay, and trying to calculate the flux. So it's possible that you can do it for a rough estimation in your as an initial design, but you must know the geometry properly to calculate the reluctance. You must know the materials property to know the permeability mu, and then you can use the equivalent circuit also to calculate or to estimate information of a motor. Okay? I think that finishes our today's talk. Tomorrow we will be looking at actually design. Okay? Is there any question up to here? Key points. Any key points that you think important to remember from here? I will suggest to recall the reluctance. Okay? Thinking about the leakage and recalling the saturation. Okay? These terms will appear again when we discuss design. So the fundamental about these terms, if you are clear, then it's easy to understand the more advanced part of the design problems. Okay? Okay, I think we'll stop here. Sorry? Yes? So BLDC and PMSM motors are actually magnetically same. Okay, so this surface type motor, which we'll be talking about maybe tomorrow. So this is called surface type. The magnets are glued on the surface of the rotor. So this motor, for BLDC, this is the rotor they use, and the stator could be could have concentrated type windings, okay, and they produces usually trapezoidal back EMF, and mostly the control of BLDC and PMSM is different. So in PMSM, you will use a more advanced control like field-oriented control or something. But in BLDC, usually it is more like much more simple control. So it could be done through the lookup table-based system. Okay, and you produce a square waveform in the inverter. Whereas in the PMSM, it's sinusoidal back current waveform you try to produce. So that's the difference. But the problem with BLDC is that you will, because you have square waveform, current square waveform, your torque is not smooth. Torque will have a lot of ripples. So if you try to use that in a car, electric car, you could have not smooth run, right? There will be a lot of vibration, noise, etc. So BLDC is very good for small power applications. Like nowadays, nearly all small motors, even in your computer fan, if you try to look at your laptop fan, it's a BLDC motor. So all small motors are BLDC nowadays, but not for large applications like traction because of that torque ripple issue. Yeah. Any other question? Yes, please. Yes, so when your rotor is rotating, so the magnetic circuit only can look for only particular position, right? If rotor changes, if the rotor is rotating, it cannot account for the rotation. Okay, so the equivalent circuit, magnetic equivalent circuit is good, similar to magnetostatic analysis in finite element, where your rotor you consider only for a particular rotor position. If you want to see what's happened in a different rotor position, you have to redraw the whole circuit, okay? So not very good to account for rotation equivalent circuit. Okay? Yes. Displacement current in the, usually for, you mean the Maxwell's displacement current, right? So these motors, especially motors type electromagnetic applications, the frequency is relatively low, right? We only make maximum, even if we take the high speed motors, the frequency is only a few kilohertz. Okay, so at such low frequency, displacement current is the main performance, no effect at all. So you consider the electromagnetic as a field, not as a wave. Okay, but if we go for very high frequency power electronics, such as the silicon carbide or the this GAN type converter or inverters, where your switching frequency could be 100 of kilohertz, even they're talking about megahertz. So if you have such high switching frequency, then your the harmonics produced by the PWM could be in up to very high megahertz. Then they start to behave, those harmonics may start to behave like a wave, okay, magnetic wave. And then maybe displacement current could have some effect, especially in your cable, in your insulation, etc. Because the displacement current is more about your insulation property. It can affect the insulation property of the cables, conductors, etc. through this partial PD, right? So those type of effect can become severe. But for conventional motors or even up to few kilohertz, it is can be ignored. Okay, all good. I hope you have liked it, and I will hope to see you tomorrow with more information or more discussion on the design, exact actual PMSM. Okay, yeah, thank you. Just on time.
Yeah, next session will start by 2:15. Okay. Yeah. See, you can have lunch at Kalam Hall, right? We'll come back by 2:15. Next session topic is modeling and simulation of electric machine. Okay. Everyone have laptop? How many participants having laptop? Can you whenever you want to solve the problem, right? What it required? Suppose there is a 1 hour time is there for solving the issue. Minimum 40 to 50 minutes you have to spend on characteristics of the actual system, right? So after that, see, based on the characteristic, as an electrical scholar, your job is you need to identify the needs. Once you know the how system is suffering with particular parameter, if you know, it is not a big deal to control. But see, issue is always we are focusing on control. We are missing the things. If you want to control something, what it required basically, in today's session we'll try to focus. Right? If you want to solve the problem, you have to define the problem clearly. You have to spend minimum 40 to 45 minutes to define the problem. That's why what we are doing, we are going through literature survey. Many of the scholars, they are doing PhD, right? But students are spending less time on the review. Dynamically, we need to, day to day, we need to update with, review the topic. Any concept is there, any updation is there, you need to concentrate on, say, problem definition clearly. Once you know problem definition clearly, it is not a big deal to find the solution, right? But thing is, we are doing reverse. We are spending less time on the review. We are focusing more on getting new things, right? How to do modification. This is the lagging, right? So in today's session, I will try to provide the philosophy behind why modeling is required, right? If you know this philosophy, right, as electrical scholar, burden on the scholar will come down. Many of the engineers, particularly electrical engineering scholars, they are suffering to understand the concept. This is the major issue, to understand the actual system behavior. Once you know, see why they are not understanding. Even see, textbooks are there, resources are there, papers are also available. Why people are struggling? Reason is they are going through the theory. You got my point? They are taking papers or textbooks and they are going through the theory. They are not depending on the mathematics. The beauty of electrical engineering is for each and every concept we are having mathematical support. If it depends on the mathematics, right, it is not a big deal to understand the behavior of the system. Right? That is the logic behind the modeling. First, we'll try to focus on modeling. What is the necessity of modeling? See, if you want to develop something, modeling is nothing but mathematical representation of actual system. Right? See, once you know the mathematical model of the actual system, we can easily extract the characteristics. Once you know the characteristics, what is the next step? We can easily develop the controller. That is what we discussed morning, right? See, particularly our system is what is the nature of our system? Permanent magnet synchronous machine. It is a complex system. It is a AC system, right? Without taking transformation techniques, we cannot develop electrical equivalent model, right? So in today's session, I will try to explain key points for developing the mathematical model. What is the necessity of transformation technique? What is the significance of control system, right? Control system, it is not a separate subject. It is a part of the system. If you know the characteristics of the actual system, we can easily adopt the method. Whenever you want to adopt particular control method, right, that method will come from the actual system characteristics only. That is, see, right, in today's session, I will try to explain concept through mathematics so that you will get more clarity. What is the beauty of mathematics you will get. Next, one more important thing is, before starting actual session, right, particularly for electrical scholars, mathematics, it is not a subject, it is a language. Each and every concept, each and every topic, we need to understand through mathematics, we need to analyze through mathematics, right? We need to develop the control logic through mathematics. If it depends on mathematics, see, burden on the scholar will come down. Everything, mathematics will give clarity. Once you are having mathematics for a particular system, you will get more clarity about the concept, right? So before starting actual session, I want to ask one important question. What is the basic significance or what is the basic need of the controller? What it will do controller? Suppose I want to control the PMSM machine. What it will do exactly, controller? Not only for PMSM, in general, in electrical system related case, take any system related case, what is the need of controller? What it will do exactly? Desired output, okay. Any other? Any desired output. What is the need of controller? Try to reduce the error. Okay. Any others? Okay. Any other? What is the need? See, my job is, I'm telling, my job is, I will try to mostly concentration on mathematical model and control point of. Madam will take care, Professor Rukmini Datta will take care about the design part. Right? There are three parts are there in this workshop. One is design of the PMSM machine. Another one is developing the mathematical model of PMSM machine and developing the control methods, field orientation, director control and model P2 control method. There are three categories are there in this workshop. So complete morning session will take care by the Professor Rukmini Datta. She will concentrate mostly on design of the magnetic circuits. My job is explain the significance of mathematical model and simulation part as well as director control FOC DTC method I will try to explain. So question is, what is the need of controller, particularly for electrical system? Desired output. Okay. See, thing is, if you take any electrical system, by nature, all are in nonlinear condition. This is a very important thing. See, even though by taking proper precaution while designing the machine, we cannot develop linear systems. That is the issue. You got my point? Even if you take PMSM machine, DC machine, synchronous machine, induction motors, basically all are nonlinear in nature. Right? By adopting the proper controller, we can bring into system into linear. That is what we are doing in field orientation control. Once system is linear, advantages particularly in aerospace application, electric vehicle application as well as in robotic application, their requirement is instantaneous torque control is their requirement. Right? See, if you are unable to control torque instantaneously, we cannot control speed or position instantaneously. See, what is the Newton's law? See, if you want to do something, it required force. If you want to change the state of the object, according to Newton's law, it required force. In case of drive mechanism, see, what is the basic definition of the drive? Drive is a mechanical energy producing device. Whether it is electrical drive or mechanical or hydraulic drive, basically drive is a mechanical energy producing device. By using this mechanical energy, we can pull, push, we can lift, right, based on the application requirement. We can roll the material also. Clear? See, important thing is, see, whenever you want to model something, first we should know the characteristics of the actual system. Whenever you want to understand the characteristics, we need to take mathematics. By taking in first, see, up to 4 o'clock, I will try to explain key points. I will try to explain what is the philosophy behind the need of modeling. Once you know this philosophy, it is not a big deal for electrical scholars to develop the simulations. There are standard universal equations are there. If it depends on the universal equations, right, it is not a big deal. Many of the scholars, they are thinking that, sir, I am unable to develop the field orientation model, Simulink model. I am unable to understand the DTC, MPC methods, right? These all methods, they are proposed based on the actual system behavior. Without knowing the system behavior, we cannot, right? See, the need of controller is practically our systems, DC machine, induction motor, synchronous machine, all special machines, SRM, PMSM machine, BLDC, all are in nonlinear nature. Now question is, how we can say it is nonlinear? What is the base? How we can decide system is a linear or nonlinear? Anyone? Anyone else? See, whether student is good or not, how we can decide based on the CGPA. CGPA is the outcome of the performance. You got my point? See, with respect to motor side, what is the outcome? What is the expected output parameter of the motor? Torque. Based on the torque profile, we can decide order of the system. Right? We don't have any option. We don't have any freedom. Right? See, particularly, see, as a faculty, what we'll see while deciding the
project groups or while deciding the something, right, we'll take priority of the CGP only. No option for us, right? CGPA is the outcome of the student performance. So as an electrical scholar, whenever you want to control something, you have to understand what is the expected output of the system, right? Basically, motors are torque producing device. Any motor, whether it is a DC motor or induction motor or synchronous machine or PMS or any special purpose machine, basically motors are torque producing device, right? Based on the torque profile, we can understand whether it is a linear mode or non-linear mode. We can easily, without any control mechanism. See, all systems basically are in all are in non-linear nature, right? First, we'll try to in first this session. I will say in this session, first initially we'll try to understand how to extract the how to extract the order of the various electrical machine. We'll try to concentrate. After that, whether it is a linear or non-linear, we'll try to identify. It is a complicated system, right? What are the challenges, right? How to overcome? How we can overcome our system? Our system is a complex system, AC system. How we can overcome? It is a non-linear system. We need to adopt initially we need to adopt transformations. Transformations will not give 100% solutions. Many of the scholars, they are thinking that by adopting Clark transformation, Park transformation or cross transformation, problem will solve. These transformations will reduce the complexity, but it will not bring the system from non-linear to linear. This is very important. Please try to understand. Transformations never will give solutions to convert the non-linear to linear system. You need to adopt technique, engineering technique, that is called scheme, control scheme, field orientation scheme. It is a very beautiful scheme, right? By adopting field orientation scheme, what will happen? Complex system, AC system, induction motor or any other motor characteristics will transfer from higher order to first order, linear mode. First order nothing but linear mode. Once it is linear mode, instantaneous control is possible. Instantaneous control is more demand in robotic application, aerospace application, as well as wherever you want to change the dynamics of the machine instantaneously, speed or position, right? It required your torque must be in linear mode. If it is not in linear mode, it will take delay. Settling time will take time. System will not settle immediately. We cannot change the position or speed immediately if it is in non-linear mode. Clear? So, see, first in today's session, what is the need of electric motor in transportation application? We'll try to focus. After that, see, whenever you want to control the motor, right? As an electrical scholar, you need to identify control variables. System to system control variables, it will change. But our system is electric drive. Whether it is a DC motor or AC motor, any electrical machine, if you adopt for producing mechanical energy, it will come under electrical drive category. In electrical drive category, we see there are two standard control variables are there. What are the standard control variables? Beyond that, nothing. We cannot do anything. You have to concentrate always, whether it is FOC or DTC or MPC, right? You have to target always that particular variables, right? Anyone, what are the control variables in electric drives? What we are going to target? Flux and what is the reason? Flux and torque, these two are the target variables. Whether it is a DC drive or AC drive or special machine also, we don't have any option, we don't have any freedom, right? Why we need to target torque and flux? Anyone? You got my point? Question, this session, please start understanding. You should not feel it is only one direction. Energy should be travel by direction, right? That's why people, they are adopting electric drive in vehicle application. Advantage is whenever you want to deaccelerate, you need to operate machine in generating mode. Energy is coming back and, right, delivering power to the auxiliary batteries. That option you won't get in IC engine based vehicles, right? That is the special feature you can get if you adopt electric machine in vehicle application? Anyone? See, my question is very simple. Control variables for electric drive is torque and flux. Our target variables are always torque and flux. What is the reason? See, with respect to customer point of view, with respect to application point of view, their requirement is always position and speed. They don't bother about how much torque is generated by machine, they don't bother. Right? As an electrical scholar, you need to bother about what is the torque generated by the machine. But with respect to customer point of view, right, he will see always what is the speed of room fan. They will bother about the speed only. They are not bothering about how much torque is generated by the machine. You got my point? So whenever you want to satisfy the customer, essential thing is, as an electrical scholar, you need to take care about what is the torque generated by the machine. Reason is, position is depends on the speed. Whenever you want to change the speed, position of the shaft, you need to change the speed. Whenever you want to change the speed of the shaft, what is the cause component? As electrical scholar, if you depends on the cause and effect relationship, as per Newton's law, it is not a big deal to understand the what is the input to the controller, what is the expected output of the controller. It become very easy. Why? Because in next session, we need to understand the control hierarchy. Next topic is control hierarchy. Control hierarchy is fixed. In our campus, what is the hierarchy? We are following. Any institute, they are following hierarchy. What is the hierarchy? What is the hierarchy? Director, deans, next. HOD, fine. Next. Faculty, next. Your hierarchy is fine, but sequence is not correct. Top priority is students. You got my point? Top, based on the student requirement, right? See, they will, HOD or timetable in charge, they will take care about the faculty. They will allotted particular faculty to meet their student requirements. To meet their requirement, they will allotted faculty, right? Faculty has to satisfy the student requirement. Otherwise, students will struggle like anything. If students are struggling, immediately HOD will see, students will give complaint on the HOD, HOD will give complaint to the deans, deans will forward the complaint to the director. This is the procedure. Right? Top priority is you need to take care about the students. But actually, director is not working effectively. Deans are not working effectively. Most of the time, see, students are working effectively. As a faculty, you have to show the path to minimize the time. Whenever you want to transfer the energy, all materials are available in YouTube, right? But as a faculty, you have to show the shortest path to reach the destination with less time. So that student will not feel as a burden. Right? We can easily transfer the energy to the students so that students feel very happy, right? If you provide shortest path. As a faculty, I will depend always on mathematics. I don't have any option. Mathematics and characteristics. If it depends on mathematics and characteristics, it doesn't require any textbook. No need to follow any textbook, right? By taking 2 or 3 examples, we can easily explain the concept, right? In today's session also, right? Based on the Newton's law, we can understand, see, what are the control variables, particularly in electric drive, will identify. These variables will not change. Even though your system is, even though your mission is changes, target variables will not change. Please try to understand. This is very important, right? See, reason is, and basically motor is a torque producing device, right? See, by controlling the torque, we can able to control the position or speed. That's why, as an electrical scholar, you need to target torque. But issue is, while controlling the torque, by adopting the flux control or field control, advantage is number of variables involved in the torque expression will come down, right? So, I will tell what is the significance of, initially I ask controller, right, question, still it is not completed. Why controller is required? Controller, by adopting the controller, with controller and without controller, difference is system order is changing. Initially all are in nonlinear mode. By adopting the control mechanism, order will get effect. If order is decreases, definitely dynamic response will improve. The ability of the closed loop system is, right, it will reject the disturbance. Primary significance of controller is it will minimize the overall system order. If order is decreases, control become very simple. Dynamic performance we can improve, right? So example, simple example, what is the mathematical model for, see, by taking this example, I will try to explain. This is called universal torque expression. This expression is applicable for all electrical machine except reluctance machines, right? DC machine, this equation is applicable. Induction motor also, this equation is applicable. This equation, see, this equation is applicable for all electrical machine. It is called universal torque expression. This expression is applicable except switch reluctance motor or reluctance torque machine. Except this one, for all other machines, this expression is valid. So by using this equation, we can understand, right, what is the need of controller, particularly if system is a complex system. If it is a AC system, what are the challenges? Why? But see, even though complexity is more, right, why people are liking AC machines, right? We'll by taking examples, we'll get more clarity about this part. After that, see, before break, I will give small assignment. You have to do simulation, so that you will get clarity what is the significance of transformation. Many of these scholars, I am telling, still they are getting confused. What is the basic difference between the magnitude invariant and power invariant in transformation, right? At the end of today's session, you will get clarity what is the difference between magnitude variant and power invariant in transformation technique, right? Next, one more important thing is whenever you are adopting transformation technique, without knowing the nature of the actual system, we cannot. Please try to understand, transformation methods also completely, the logic behind to develop the transformation also, it is completely based on actual system characteristics. If your system is a three-phase system, you need to adopt three-phase to two-phase conversion. Suppose your system is excited with pure sinusoidal signal, fine. According to that, you need to take zero sequence component 0 in transformation technique. Otherwise, if your system is excited with non-linear signals, right, non-sinusoidal signal, right, I want to ask one important. In between, I will ask so many questions so that, why? Because afternoon is a very tough time to transfer the energy to the audience. Very big challenging after lunch break, so that I need to ask questions. Why sinusoidal signal is reference for electrical scholar? What is the reason? Why we need to adopt sine signal? Why we need to apply sine signal to the motors? Any reason? Why sine is reference for electrical scholar? Why not triangle? Why not trapezoidal? We are not applying trapezoidal or triangle waveform. Our requirement is always sine. What is the reason? No, Fourier series mathematics will come later. First we need to take care about the physical system behavior. Sorry? Anyone? That is mathematics. We are not applying integration, differentiation to the fan, right? We are applying sine signal. Simply we are applying sine signal. Generation? Correct. See, for electrical engineering, for mechanical engineering, what is their reference for mechanical engineering? Wheel. Circle is their reference. Why? Why our vehicle tires are in circle shape? minimum losses. Centrifugal forces acting on rotor surface, if rotor core is in circle shape, your wheel is in circle shape, centrifugal forces acting on the rotor surface is very less. Friction is also very less, right? So that we can minimize the losses. If losses are less, reliability will increase. More time you can operate. Whenever you want to operate the same system, more time you need to take care about heating effect. Everything, all systems are designed based on the heating effect, minimizing the heating effect. No option. All electrical systems, mechanical systems, electronic systems, see, they will design to minimize the heating effect. Right? So, if your rotor core is in circle shape, we don't have any option. You need to arrange the conductor in circle shape. If conductors are in circle shape, right? See, if conductors are arranged in circle shape, right? For understanding, there is a north and south pole is there. This is the nature of magnetizing flux. This vector, this is the nature of magnetizing flux. Clear? This vector is looking like constant with respect to participants. Now, see, the length of this vector is looking like constant, but if I rotate in circle shape, right, with respect to me, so if I stand here, this vector is looking like dot initially, right? If I stand here exactly here, this vector is looking like dot. If I come here, vector length will increases, right? Exact perpendicular maximum, vector length looking like maximum. After that, if I complete off cycle, again it will come back to 0. What it means? See, whenever person is rotating with respect to audience, it is looking like constant. Vector length is looking like constant. But see, when conductor is rotating in circle shape, pure circle shape, right? Same vector is looking like sine waveform. Magnetizing flux is looking like, with respect to rotating conductor, it is looking like alternating. Circle is nothing but, sinusoidal is nothing but less heating effect. Whenever your conductors are rotating in pure circle, heating effect is less. So that we can operate more period, more time. Reliability is good. Right? If it is rotating in circle shape, we'll get sinusoidal. No option. Right? That's why this is about generating mode. If you apply sinusoidal signal to the machine, your rotor also rotating in circle shape, pure circle. Nothing but losses are less. You got my point? Sine, both. If conductor is rotating in circle shape in generating mode, it will produce sinusoidal voltage. Whenever you apply the sinusoidal voltage to the system, your mechanical system will rotate in pure circle, so that heating effect is less, reliability will increases more. That's why, see, electrical engineering or mechanical engineering, their reference is circle. Circle is nothing but technically sinusoidal, Vm sin omega t or Vm cos omega t. Right? So, by taking this universal equation, initially we'll try to focus on what is the order of the actual system. Based on the potential element, what is the output of the element, based on the output element produced by the system, we can decide the order. Right? So, here whenever you want to decide the order, as an electrical scholar, you need to understand how many variables are involved in the equation. Right? In case of DC machine, the beauty of DC machine is, because of commutation action, this delta become 90. Am I correct or not? Delta, space displacement angle, this is about magnetizing flux, this is about armature flux. Right? What is the space displacement angle? 90. Is it variable or constant? It is a constant. You need to take precaution. By taking precaution, by taking interpoles, by taking right, proper precautions, even load torque is increases, even burden on the machine is increases, this angle will not change. Like that, you have to design the machine. By taking care about the design, right, we can maintain constant. If it is a 90 degree, advantage is, what is the advantage? How many variables will come down? Xi s, xi r. This equation we can replace. We can write T equal to xi s is nothing but stator flux, xi r is the rotor flux, right? Xi s is mainly because of field current. So, right, stator flux we can write in terms of field current, rotor flux we can write in terms of armature current. These two are responsible for producing the field flux as well as armature flux, right? So finally, how many variables are there? These two components are flowing through the different windings, field winding and armature winding, different coils. These two are called state variables. These two currents cannot change instant to instant without adopting control mechanism. You got my point? Why? Because time constant is different. By adopting the control mechanism, we can able to minimize the order so that time constant will come down. With controller, without controller, time constant it will regulate. System response will regulate. So by taking this equation, now what is, how many variables are there? There are two variables. What is the order? Second order. Is it linear or non-linear? Basically it is non-linear. Now you can, how we can convert non-linear to linear? By nature, DC machines are, motors are in non-linear nature. How we can change the mode? How we can change the order of the system? See, if it is a non-linear, it is not so easy to improve the dynamics instantaneously. Then no option. We need to go for control mechanism. We have to adopt method. By using concept, by using different schemes, we can able to convert from non-linear to linear. Right? What is the method in general we are adopting? There is a popular method is there for DC machines to convert non-linear to linear. What is that method? You know about armature voltage control method? You heard? What is the beauty of this method? In armature control method, what is the first step? We are, throughout the operation, we are maintaining field current as a constant. If it is a constant, we not only maintaining constant, we are maintaining the field current at rated condition. Maximum flux we are maintaining in the system, right? So that field current is constant and rated value, so that torque equation become, so armature voltage control method. This is the logic. This is the control scheme. Many of the scholars, they know the method, but they are not concentration on what the logic behind this method. You have to analyze in detail, so that you will get clarity about what is the significance of control system. Right? Whenever you want to adopt armature control method, it is a scheme, control scheme. You should know actual system behavior. Based on the actual system behavior, right? Basically it is in nonlinear condition, right? So by maintaining this component as a constant, by regulating, by maintaining IF as a constant, we can convert it to nonlinear to linear. But issue is which method we need to adopt? Armature control voltage. Right? If you adopt armature control voltage, nonlinear system become linear. Next, one more important thing is armature control method, right? By maintaining field current in DC systems are very easy. Right? So whenever you want to maintain IF constant, you need to apply constant VF across the terminals. Right? Now, see, tell me, what is the order of, now DC motor basically in second order. What about order of the induction motor? 7. Why 7? Why order is 7, induction motor? See, stator side, this is called resultant stator flux. After interacting A phase, B phase, C phase, you will get lambda S. After interacting rotors, A phase, B phase, C phase, you will get lambda. Many of the scholars, they are getting confused why rotor circuit is a 3-phase circuit. Even though it is looking like squirrel cage, right? If stator side number of poles are 4, automatically same number of poles will induce on the rotor side. If stator side, if you excite with 3-phase system, rotor side also 3-phase currents will flow. 3-phase voltages will induce on the rotor side. 3-phase currents will flow on the rotor side, but frequency different. Frequency, rotor current frequency, rotor voltage frequency is completely different than stator. Right? if it is a three-phase stator side winding is in three-phase circuit, rotor side also you will get three-phase voltages and three-phase currents. Clear? Now see, so stator side three-phase, 3 variables are there. Rotor side also 3 variables are there, 3 plus 3. Next, one more important thing is, in case of induction motor, we don't have any commutator brush combination. We cannot maintain delta 90 degree. Because of this reason, delta is also variable in case of AC systems, right? So it is also variable. So 3 plus 1, what is the order? 7th order. But why people are motivating induction motor? What is the reason? Even though it is mentally it is a very weak, right? Torque profile is in 7th order. Why people motivating all industry 90 to 95% application, they are adopting induction motors only. Applications of DC motor, except India, in foreign countries no one is using DC machines. In traction application also, right, coming 4 years their target is replacing DC series motors with induction motor. Their target. Coming 4 years definitely they will replace DC series motors with induction motors using vector control methods, field orientation method. What is the reason? Main reason is induction motors physically very strong. No brushes, no commutator, machine size is also very compact, but DC motors are very physically very complicated, very lazy also, physically very, maintenance is more, brushes you need to take care. The lifetime of induction motor is 70 to 80 years. Continuously you can operate 70 to 80 years, no issue, no maintenance. But if you take DC machine, issue is maintenance is required. We cannot operate more than 15 years. Lifetime, maximum lifespan is for DC motor is 15 years, 1-5. For induction motors, 70 to 80 years we can utilize, right? Next, come to conventional synchronous machine. What is the order of conventional synchronous machine? What is the torque profile? What is the torque profile of synchronous machine, conventional? See, our main focus is, our main final objective is synchronous machine, PMSM machine. First, see, if you want to understand the characteristics of the PMSM without knowing the fundamentals, it is very difficult. It is a 4th order system. Rotor poles are excited with DC, conventional. Current, it is not a variable. Under steady state condition, current will not regulate, right? So stator side three variables are there, rotor side there are no variables, right? Next, delta is a variable in case of synchronous machine. 3 plus 1, it is a 4th order. So finally, even though it is a 4th order, compared to induction motor, order is less, but practically conventional synchronous machines, motors no one is using in practical application. Reason is physically very big, brushes are there. If you want to transfer the energy from DC to rotating part through brushes, maintenance is required. Speed constraints is there. We cannot go beyond the 1500 RPM. Conventional synchronous machine. There are a lot of limitations are there for conventional synchronous machines, right? So now there are 3 machines. Beyond that, nothing is there. Please try to understand. These 3 operating principle of these 3 motors we can understand by taking single equation. There is a universal equation is there, speed expression is there. If it depends on the speed expression, we can understand what is the logic behind the each machine, right? Now I want to ask one important question. The expected output of any motor is a torque. If you want to produce the torque, what is the essential condition you need to satisfy? There is a logic is there behind the all machines. Behind the torque producing principle, concept is same. DC motor concept is same. Way of generating torque in all machines, logic is same, principle is same, but procedure is different. If you want to produce the twisting force, what it required? What it required in all machines, DC machines, induction motor, PMS, even PMS also, there is a common principle is there. What is that logic? interaction, relative motion must be 0. Relative motion between this xi s and xi r must be 0. At any moment of the time, at any instant of the time, you need to take care about the relative motion between the stator flux and rotor flux. Relative motion is 0 with respect, see what is the speed of participants all are sitting, speed of the participants 0, speed of the right faculty also 0. So what is the relative motion between the faculty and participants? 0. So that we can interact effectively. Otherwise, if faculty is stationary, participants are running, we cannot transfer the energy. We cannot convert also. Whenever you want to convert energy, first you have to transfer the energy. First, initially, you need to transfer the energy. After that, based on requirement, we can convert the energy levels. That is what we are doing in all electrical machine. In DC machine, your commutator will take care about the relative motion. In case of induction motor, your slip will take care about the relative motion. Even in case of synchronous machine, your synchronous reactance will take care about the relative motion. All will take care. Right? In all machines, common logic is you need to take care about the relative motion between the stator flux and rotor flux. Relative motion must be 0. If relative motion is 0, both will interact. Based on the requirement, it will produce the twisting force. Now, question is very simple, right? My question is very simple. Take no load condition and load condition. What is the difference between load condition and no load condition with respect to magnetic circuit point of view? Anyone? Anyone from the participants? You got my question? First try to understand question. This is important. Later you can answer. Sorry? No, relative motion will not disturb. If relative motion is disturbed, everything will spoil. Machine will not generate the torque. Relative motion will not get disturbed at any moment of the time. With respect to magnetic circuit, flux is constant, but flux density will get affected. This is important. Please start understanding. See, I think, see in undergraduate course, I think while studying the electrical machine, you have gone through the Fleming's left-hand rule, right-hand rule, right? See, the principle, the logic behind to propose, these all are methods. They have proposed this method, Fleming's left-hand rule or right-hand rule. See, these all are methods they have proposed based on the basic principles of the machines. If you follow this method, what will happen? We can minimize the time. We no need to know, see what is the happening inside, what is the direction of current, direction of flux density, whether flux density is changing or not, we no need to bother about. Simply by applying Fleming's left-hand rule, you will get what is the direction of twisting force. Right? See, Fleming's left-hand rule or right-hand rule, they have proposed based on the flux density concept. Right? Flux density is a uniform in no load condition. Under no load condition, flux transferring from north pole to south pole, if you verify, you can take any sample in between. Under north pole influence side or south pole influence side, you can take any sample and verify the sample flux density per flux per area. If you verify, it is a uniform. But once you apply the load, flux density will get disturbed. Flux density become non-uniform. Actually, non-uniform flux density is required to produce the twisting force. Please start understand. But issue is sometimes your core may enter in saturation. If you apply more load, what will happen? Why machine is not generating required torque? Reason is flux density, it is going beyond the rated value, right? Even see, it will enter in saturation. Once flux density is enter in saturation, machine will not produce the torque. Even if you increase the burden on the shaft, machine cannot produce more amount of the torque. That is the issue. If torque is increases, flux density changing. If flux density is increased at one point, see one zone, what will happen? Upper zone flux, let us assume that flux density is increasing. Bottom flux density is decreasing, what will happen? Upper side, core will enter in saturation. Your magnetic circuit may enter in saturation. If it is entering in saturation, definitely a machine will unable to produce required torque. This are also challenges. That's why we should not apply the load torque beyond the 120% or 130% of the rated torque, right? So here issue is, finally from this slide, what are the conclusion? We can understand, see the order of DC machine is very good. It is in second order. By adopting simple armature control method, we can bring into linear mode, right? If it is a linear mode, we can improve the dynamic response instantaneously. But problem with induction motor and synchronous machine, order is more very complicated. If you want, whenever you want to control the torque or flux, it required more number of feedbacks. If torque is depends on 7 variables, we don't have any freedom. You need to take 7 feedbacks to control the torque effectively, right? In case of synchronous machine, order is 4. We need to take 4 signals feedback from the system so that we can control the torque. If number of feedbacks are more, design of the Kp and K value, it is not a simple task for if number of feedbacks are more. If number of feedbacks are increases, control point of view, it is very complicated, right? That's why. But thing is, people are motivating towards AC machines, induction motor. Why? Because no brushes. Reason is, right, no brushes. Before 1970s, most of the engineers or researchers, they design engineers as well as control engineers, they were focusing on control the DC motor before 1970s. After 1970s, field orientation method, vector control method they have proposed. Under vector control, in 1970s they have proposed field orientation control in 1970s. After proposing field orientation method, the behavior of the induction motor, characteristics of the induction motor is similar to DC machine. It will offer same character. Whatever characteristic is offered by the induction DC motor after armature control method, same profile you can expect even if you adopt induction motor in practical condition. That is the beauty of field orientation method, right? But issue is, see, mentally induction motor is very poor. Physically DC machines are very poor, but industry people, they are giving top priority for physical characteristics. Whether person is physically fit or not, they will check. If student is fit, even though he is average student, he can able to sit in the exam hall continuously 3 hours, he can able to at least write 3 or 2.5 questions, he can get minimum C or B grade. Even though person is excellent in see, subject wise he is excellent, but he is unable to sit in the exam hall because of physical characteristics. He cannot write exam hall continuously more than half an hour. What is the issue? He cannot get any grade. After examination he will not get. But good thing is he can answer all 5 questions, but he cannot get grade. So because of this reason, industry people first they will give top priority for physical characteristics. So physically who is fit out of these 3? Induction motor. Later I will explain what is the issue with induction motor. Why induction motor they are going to replace with PMSM machine. I will explain in detail. You got my point? See, first initially their target is induction motor. Initially they will focus on induction motor in 1970s. Why? Because system, it is a very rugged system, no maintenance, very compact. Particularly in electric vehicle, aerospace application or satellite application or submarine application, there is a limited space is available for drive system. Right? With limited space, if you want to produce more power, you have to go for PMSM machine. No option. Right? Clear? So this all are about torque equation. Later after completion of modeling you will get clarity about. See, by seeing all are looking like very complex, but if you depends on the mathematics step by step, if you go step by step, definitely you will get clarity about this equation. Finally, right, this is about induction motor equation. If you observe the induction motor torque profile, there are 7 variables are there in terms of currents, right? 7 variables. Now if you take synchronous machine, conventional synchronous machine, there are 4 variables are there. If you take permanent magnet synchronous machine, final torque expression, there are 4 variables are there. Right? So PMSM also, it is a 4th order system. Right? What are the challenges? See, before explaining these challenges, everything, I want to ask one question, one important question. Why? Because many scholars already, they are going to submit, some scholars, they are going to submit thesis, some students already completed PhD, right? What is the need of transformations? You know about transformations? 3-phase to 2-phase conversion. What is the need of transformation? To reduce the complexity. No. This one, complexity will come later. Sinusoidal to DC, no. There, this all are, see, if you adopt transformation, finally, 3-phase to 2-phase variable, right? 2-phase AC to 2-phase DC. This is all are fine. What is the basic need of transformation? No. Understand the behavior very good. Any other? Where they are adopting these control transformations? With respect to control point of view. These transformations are so important with respect to control point. With respect to control point, what is the objective? Whenever you want to control something, first you have to get the feedback. Without taking feedback, we cannot control effectively. You got my point? By adopting transformation, you will get actual system behavior with less number of variables. You will get clarity about, see how system is behaving in detail, you will get clarity, right? See, this is a very popular technique, engineering technique. What is the use of this technique? You know about this one? This is corner mirror. Particularly, see, in hill areas wherever sharp curves are there, they are adopting this technique. You got my point? What is the use of this technique? It is a technique, engineering technique. It is like transformational. Transformation also, it is an engineering technique. What is the use? Mirror. This one, corner mirror. See, let us assume that, take example, here there is a sharp curve is there. Clear? So now this is the position of our controller technique. This is engineering technique, right? Now our reference person is here. There are 2 vehicles are there. This is A vehicle. This is about B vehicle, right? Our reference person is sitting inside the A, right? Now see what he will do. This reference person, whenever, see, let us know that there is no technique. This one, what will happen? What is the option for controller? Whenever he want to turn the path, no option. There is no mirror. He has to reduce the speed. If there are n number of curves are there, wherever curve is there, he has to bring the speed less. He has to reduce the speed. So see, without knowing the information, also we can operate the system, we can operate the vehicle, but issue is it will take long time to reach the destination. You got my point? See, without transformations also we can, but thing is dynamic response will not improve. We cannot, see, it will take long time to reach the steady state. So by adopting this curve, by adopting the wherever curve is there, sharp curve is there, by adopting this engineering technique, first thing is we'll get information. Whenever we are crossing the curve, before crossing the curve, you will get information. You can get the information whether any vehicle is coming opposite way or not, you will get clarity. If there are no opposite vehicle, you no need to minimize the speed. You can go as possible as speed, you can go and you can reach destination. If any vehicle is there, you have to reduce the speed and you have to control the vehicle speed and you have to cross the vehicle, right? So here mirror is a technique. It will give information about actual system information. It will give, it will pass to the controller. Your transformation technique also will pass the information to the controller. Actual signal, actual system behavior, right? It will transfer to the controller without losing any property. You got my point? If opposite any car is there, reference person can observe whether it is a car or truck, he can observe. It will give, it is a mirror, same reflection only, right? Any bicycle is there, no need to reduce the speed. You can go. You can go. Any big truck is there, you have to stop. Any luggage, big truck with luggage is there, right? Whenever you want to climb, you have to stop the vehicle and you have to allow big truck first. Then after that you have to travel. Am I correct or not? This is the standard procedure they are following in transportation case, right? So here also, by using this transformation technique, Clark transformation, Park transformation, cross transformation, right? We can, without losing any property, we are getting the information from the complex system. Basically, see, our system is a complex system. It is a three-phase system, right? See, if it is a three-phase system, what we are doing? You need to adopt, no option, you need to adopt complex vector concept. That is called space vector technique you need to adopt. This transformation, the logic behind this transformation is based on the space vector technique, they have proposed this method, right? What is space vector technique? What is space vector technique? I'm not talking about PWM. Space vector PWM is different. I'm talking even space vector PWM is PWM concept they have proposed based on the space vector technique only. Space vector technique, other name is complex vector representation. Any vector in space we can represent into two variables. One variable we can take on x-axis, another variable we can take on y-axis. You got my point? Let us assume that our system is a complex. In our AC system, the nature of magnetizing flux is always rotating in space. It is always rotating with supply frequency, speed. If supply frequency is more, speed of the vector is more. Clear? Now, thing is, right, this vector, we can represent, right, alpha axis or effect of this vector we can express in terms of alpha axis as well as beta axis. That is called complex vector representation. What is the mathematical operator for complex vector representation? E power j. You know about this operator? It is a very beautiful operator. By adopting this operator, we can understand what is the logic behind cross transformation, Clark, Park, everything we can understand. Simple. Only your job is you need to, this is important, plus or minus e power plus or minus j. Next, here angle, how much angle? Theta. By using this operator, we can convert, we can see the nature of complex system. Our system is a three-phase or multi-phase, more than, even if it is a five-phase system also, right? By adopting this transformation, finally we can transfer the signal into two variables. You got my point? Now question is, see, many students or participants, they are interested to understand the field orientation control, direct or MPC control, predictive control. See, whenever you want to develop simulations in particular control, why this logic is required, why these transformations are required, are so important. Why you have to think, so that you will get more clarity. Why, what, how, these three parameters you need to take. As a research scholar, if you take care about these three parameters, your problem becomes simple. Clear? Now question is, my question is, see, I will explain using this operator how to convert three-phase to two-phase, power invariant, magnitude invariant. Anyway, today assignment is, you have to do this simulation in hostel, right? You have to develop this simulation for three-phase to two-phase, magnitude invariant and power invariant. You have to show the results by tomorrow or anyway day after tomorrow, holiday, right? You can show me on Thursday. Any doubts are there? Will help. Before doing vector control method, field orientation method, transformations are so important, right? Now, my question is, why transformations are required? Okay, fine. See, by using transformation, you will get clarities, right? We can minimize the variables. It is fine. But with respect to control point of view, how this one, how what is the significance of this transformation? Physically, please try to understand. As an electrical scholar, you need to understand what is the actual system behavior. This is so important. Based on the actual system behavior, see any needs are there, actual need is there, engineer, they have to think. Based on their needs, you have to work so that we can solve the issues. Need is, identify the need is a very big challenging for engineers. Based on the need, we can summarize the problems. If problem is a really serious problem, you have to take care. If it is a problem is not that much, you can ignore, no issue. But in AC systems, all AC systems, there is a big issue is there with respect to control point of view. What is the issue? Time varying, later time varying inductance, later will come. Time varying inductance, later. Coupling is, anyway brushes are not there, definitely we cannot maintain 90 degree. Decoupling is not possible in any machine. Anyone? Controllers will come secondary. I'm telling you, see, try to, don't focus on control side. First you need to, this session is exclusive for understanding the actual system behavior, right? So how system is behaving, right? What is the need of engineer, control engineer with respect to actual system? If you understand what is the, this one today, philosophy behind this concept, right, you will get clarity about what is the need of transformation in AC system. This transformation technique is applicable only for AC systems, complex system, not for DC or not for two-phase system. It is applicable for three-phase or five-phase or n number of phases. What is the problem with three-phase system? Mutually independent. Both magnitude and angle is control. Oh, no. No. See, in case of DC machine, there is a separate path. We don't please start understand. If you take any machine, finally there are three circuits are there. Inherently, there are three circuits are involved in the system. One is magnetic circuit, that is called field circuit. Another one is called armature circuit. Another one is called mechanical circuit. Right? Armature circuit, field circuit, and mechanical circuit. You got my point? See, before closing today, we'll try to develop one model based on these three circuits. Example, we'll take DC machine. Right? Initially, we'll take DC machine so that some students are from undergraduate only. Right? So that they will get more clarity. Right? As a faculty, I need to satisfy everyone. From basic ground to right required level, I have to teach. Right? See, issue is, take DC machine. In case of DC machine, physically there is a separate path is there for field current, and there is a separate path is there for armature current. Am I correct or not? See, by connecting ammeter here, you will get clarity about field current. How much field current is flowing to the system, you will get information. Even if you connect one more ammeter in series with armature, you will get clarity about how much current is flowing to the armature circuit you will get. Once you know the clarity about the actual system currents, it is not a big deal to control. But if you take AC system, induction motor, take induction motor, what is the nature of current passing, what is the nature of IS? What is the mathematical operating principle of induction motor, operating principle of transformer? Same. You got my point? So what is the mathematical model for input current in case of transformer? I1 equal to I0 plus I2 dash. So from this equation, what is I0? I0 equal to I mu plus IC. core loss component. Compared to magnetizing component, core loss component is only 2 to 3%. You can neglect. So what is the resultant input current? So input current is nothing but I mu plus I2 dash. Clear? Input current. See, I will rewrite here. Input current equal to I mu plus I2 dash. What is I2 dash? I2 dash is nothing but load torque. Depends on the button on the shaft, this current will regulate. Nothing but, see, the main responsibility of I2 dash is it is a torque producing device. You got my point? I2 dash is a torque producing device. What is function of I mu? It is a flux producing device. Finally, see, the main object of any electrical machine, what we are doing is we are supplying two different nature of the current. One is for magnetizing poles, another one is producing the twisting force. Nothing is there. Beyond that, nothing is there. Right? In case of DC machine, to get the required, based on the customer requirement, to get the required position or speed, what we are doing, we are generating the torque. Right? To generate the torque, you need to take care about the IA. Based on the strength of the current drawn by the machine, we can decide what is the torque producing by the machine. IA is nothing but it is a torque producing device. IF is flux producing device. This one, the main responsibility of IF is it will magnetize the core. IA is it will produce the twisting force. Right? So in DC machine, there is a physically there is a separate path is there for IF and IA. But AC machine, if you verify, right? Even though if you connect ammeter here, what you will get what is the resultant strength of the current drawn by the machine. You cannot get what is the strength of magnetizing current drawn by the machine independently, right? What is the strength of I2 dash, you will not get clarity. You got my point? That's why transformations are required. Transformations, after applying the transformation, you will get clarity about what is the magnetizing current drawn by the complex system, what is the torque producing device drawn by the complex system, you will get. Once you know the magnetizing current information and torque current information, it is not a big deal to bring the I mu and I2 dash based on the reference currents. It is not a big deal. By choosing proper Kp and K value, we can eliminate error. Nothing but reference current and actual current both are matching, then your speed will come to based on the customer required position. You got my point? Now you understood what is the need of transformation. Transformations will give clarity about, right, inherent current information you will get in detail. If you take input current, three-phase current, by taking three-phase current through ammeter, you will not get clarity. By applying the transformation, by applying engineering technique, you will get clarity about I mu and I2 dash. Right? Independent values you will get. But ammeter will give only resultant value of the input current. By applying the transformation, you will get more clarity about the I mu and I2 dash current. That is the significance. That is the significance about the transformation technique. Next, one more important thing is, see, main challenges in AC drives is eliminating. You need to focus on non-linearity. How many variables are there in the actual system? Torque expression you need to verify. If there are more variables are there, automatically control circuit become more complex. Issue is if control circuit is complex, see, execution time, particularly whenever you want to execute the logic in real time using real time controller, issue is computation time is more, we don't have option, you need to increase the sample time. You know about significance of the sample time? What is sample time? The rate at which we are executing the logic, right? See, if sample time is more, what is problem? Error is increases. See, in academics, what we are doing, we are taking feedback from the students after completion of the semester. Before last working day, the deans, they are taking feedback from the student. Who will get benefit? If you take more number of samples per semester, if you take more feedbacks from the student per semester, we can improve the quality of the education. Any issues are there, we can rectify. Right? Same, if you take more number of samples per second, we can eliminate the error. Sample time, it is not under your control. It is completely decided by the length of the sample time is decided by the length of your logic. Your logic is complicated, right? To solve a simple solution, to solve a simple problem, if you take complicated solution, sample time will increases, right? So see, if sample time, see your execution time is 10 microsecond, right? Sample time, you have to take at least 20 microseconds, fine, right? Sample time must be greater than your execution time. No option. Otherwise, if you take less sample, execution time is more. Within sample, your program is not executed, you will not get any outcome, right? See what industry, what controller is expecting, what power electronic module is expecting after completion of every cycle. If you go through this block diagram, you will get clarity. After, this is the logic. Please try to understand. This is the logic behind the advanced control schemes. Field orientation method, right? Variable voltage and variable frequency method, director control, MPC methods, right? So these logics through microcontrollers we can execute. After executing this logic through controllers, what you will get after completion of every sample time, what is the expected output? What your device will, power electronic is expecting pulse. Pulse, the expected output of the controller is pulse. Based on the requirement, based on the speed, by adjusting the duty period of the pulse, right, we can change the RMS voltage and frequency we can regulate. By changing the frequency and voltage, we can change the characteristics of the motor based on the load requirement. This is our load, right? Based on the load requirement, we can change the motor characteristics. This is a complete EV propulsion system overview, right? So our part is developing the logic. This is the logic, mathematic concept. By adopting this concept, what we can do is we can improve the motor profile to meet the load requirement. You got my point? First, see important thing. What is the important thing in this block diagram? Anyone? What is the task? There are so many blocks are there, right? Electronic controller is there, battery is there, power converter is there, electric motor is there, right? So as a design engineer, which part you have to give top priority? What are there are so many blocks are there. What is the top priority block? That's what I'm telling. You're always thinking about controller. Your focus is on controller. Top priority is how much burden is applied on the motor shaft. This is a motor shaft, right? This is the reference point. This is a reference point, right? With respect to this reference point, how much burden is applied on the motor shaft, you need to calculate. This is important. Based on the load requirement, right, you need to generate the twisting force. Torque we can control through power electronic module. We can generate and we can modulate based on the requirement. Top priority block is load. This is a top priority. This is a top priority. This is the rank 1. Right? So whenever you want to control motor, essential thing is how much burden is there with respect to, this is a reference point. With respect to this point, you need to calculate what is the burden applied on the motor shaft, you need to calculate. Once you know the burden characteristics, once you know the load characteristics, right, by using electric motor, we can change the torque profile. Load torque, TL, see, TL, it is not in your hand. The behavior of the TL is not in your hand. Please try to understand. As a controller, you need to satisfy the TL. If you want to bring your system into steady state, right, generated torque must match with load torque. This is the essential condition to bring your system into stable. Right? See, thing is, this is not in your hand. This is under your control. This machine torque, motor torque, we can control through power electronic plus controller. V by F, right? variable voltage and variable frequency method, field orientation method, direct arc, or different methods by using without taking combination of power electronic and control method, we cannot change the torque dynamics of the AC system similar to DC machine. These two combinations are required. These two combinations are essential to change the dynamics of the AC system similar to DC machine. Practically, see, whenever they want to improve the AC system performance, benchmark is DC machine. But DC machines practically it will not come to the picture. But benchmark, torque profile, everything they will compare with DC machine only. Benchmark is a DC machine. But practically all are AC machines only. In EV application, aerospace application, all are adopting AC machines. Right? So, see, in this block, top priority is load. Second, what is the second priority? Anyone? Ranking. As a scholar, you have to decide the rank. There are so many subsystems are there in this block, in this system. Second ranking is motor. Based on the load requirement, based on the availability of the space, if space is sufficient, there is a sufficient space is there, you can go for induction motor. Instead of PMSM machine, you can go for induction motor. Next, another important thing is now there are a lot of techniques are there. Without permanent magnets also they are proposing techniques. Magnetless synchronous machines through induction principle. Right? Later, see if sufficient time is there, I will try to explain some of the techniques still under research level. Right? So, we are also concentrating on one machine, right? Without brushes, right? Without brushes, without permanent magnets, we are trying to develop one machine. Later, I will explain the concept. If time is there, I will try to explain. Right? Already we collaborated with one industry. Initially they agreed, right? Officially we have not completed any MOU. Initially they agreed. Later we'll see what will happen. We don't know. Industry people, they will not. Initially they will show a lot of interest, but when come to the documentation, they will afraid like anything. Okay. We'll later, if time is there, sufficient time is there, we'll discuss in detail. Right? So by taking second priority is motor. How they will select the motor? Selection of motor is mainly based on how much power is required, power levels based on the available space. Right? More power requirement is more, less space is available. We don't have any option. You have to go for special machines. Special machines, nothing but what is the advantage of PMSM machine? Now question is, see, why PMSM machine will PMSM machine efficiency is more? What is the reason? Rotor winding, okay, that is fine. Technically, what is the excitation is not required. Sorry, why efficiency is more? Less losses. You know how they will calculate efficiency in general? You know about power factor? Can I ask one question? What is the significance of power factor? If you take power factor, there are no units for power factor. It is a factor, right? So by using power factor, we can understand what is the rate of energy conversion. If power factor is 0.9, energy conversion rate is 90%. If power factor is 0.98, see, energy conversion rate is 98. You got my point? Based on the power factor, we can decide what is the conversion of energy rate. Why efficiency of the PMSM is more compared to induction motor? Reason is, what is the reason? Ideally, I'm telling, ideally, required magnetizing current under no load condition is 0. What is the nature of magnetizing current? Practically, if you take an induction motor, what is the nature of magnetizing current? It is always working perpendicular to the voltage. If you verify the position of the magnetizing current, it is exactly perpendicular to the voltage. If voltage is here, magnetizing current is lags the voltage by 90 degree, exact 90 degrees. If it is a 90 degrees, what is cos 90? 0. Conversion rate is 0. But thing is, because of load, what will happen? There is one more component is entering the current, I2 dash. Right? Because of I2 dash, if you take care about magnetizing current and I2 dash, resultant current will come less than 90 degree. Anyway, see, this angle is more in case of induction motor because of magnetizing current. But in case of PMSM machine, technically, mathematically, if you verify the required magnetizing current under no load condition, ideal condition, it is almost 0. If magnetizing current requirement is 0, see, if you verify input current, it will come closely to I2 dash is coming closely to, see, if I mu is 0, I1 and I2 dash both are in phase. You got my point? Nothing but your input current will come closely to voltage. Nothing but energy conversion rate is more. The beauty of magnets is it will provide environment. It will provide good environment without need of magnetizing current. If you want to do any job in electrical engineering, it requires reactive power. But issue with reactive power is if you want to maintain sufficient reactive power, right? Issue is it requires magnetizing current. The drawback with magnetizing current is power factor will get poor. The issue with magnetizing current is it will reduce the energy conversion rate. But if you want to do work, it required reactive power. Both. See, by adopting permanent magnets on the rotor side, advantage is, right? See, it will create good environment. If you want to do anything, first requirement is environment must be good. If environment is good, we can able to do our job effectively. If environment is not good, right? See, lights are blinking. It is very difficult to writing the notes, right? You got my point? If lights are blinking continuously, it is very good, very bad to write the notes or to attend the classes or to understand the concept. See, whenever you want to do some work, initially you need to take care about what is the nature of, what is the strength of reactive power. That is what we are doing in armature voltage control method as well as V/F method in AC machine. In armature control method, see, we are providing good environment to the DC machines. Nothing but we are maintaining sufficient reactive power in the air gap. Right? See, the beauty of magnetic circuit is, right, if you take any dynamic machine, there is a air gap is there between stator to rotor. The nature of air gap is it will store the field energy. Almost 98% field energy is available in air gap only. Any electrical machine. If you take any electrical machine, field energy is so important. The drawback with electric circuit is we cannot transfer the electrons from one circuit to another circuit through air. But beauty of the magnetic circuit is we can transfer the energy from one circuit to another circuit through air gap. You got my point? So once you excite the stator, what will happen? Whatever electrical energy you are supplying, it will convert it in terms of field energy. Right? The ability of the air gap is it can store, it can hold the field energy. 86 to 88% field energy is available in air gap only. Now question is, what is the significance of field energy? That is what we have studied in energy conversion in all electrical machine. What is the significance of field energy? Anyone? Okay, fine. If field energies vary with respect to rotor position, then only your machine torque become finite. Field energy must vary. No option. Whatever energy is available in air gap, that energy must vary with respect to rotor position, then only you will get twisting force. This is the logic. This is the logic behind the electrical machine. This is the nature of torque generated by the all electrical machine. We don't have any option, we don't have any freedom, right? This is the standard mathematical expression applicable for all electrical machine. If you want to produce the torque, field energy must vary with respect to rotor position. Right? So there are different types of torques we can able to produce using, see, one is called reaction torque machines, another one is reluctance torque machine. If self-inductance is vary with respect to, if self-inductance is vary, I am telling inductance will play key role in all electrical machines. We are thinking that inductance is a constant. Inductance is always regulating with respect to rotor position. Clear? If rotor position is changes, inductance is also changes. Right? Field energy or co-energy, see this one, if co-energy or field energy is vary with respect to position, then only you will get non-zero average torque. If torque is non-zero, then immediately you will get acceleration mode. Your drive will enter in acceleration mode. If you take any drive, commonly it will operate in 3 modes. One is accelerating mode, another one is steady state mode, last one is final one, deaccelerating mode. Right? Accelerating mode or deaccelerating mode or steady state, it is completely under your control. Torque, based on the torque levels, right? We can able to, by controlling this one, right? We can able to control. Next, one more important thing is by remembering this equation, omega m equal to omega s plus or minus omega r. This is the standard mathematical expression, right? Speed of the rotor expression. This equation is applicable for all electrical machine. By taking this equation, we can understand what is the logic behind DC machine, what is the logic behind induction motor, what is the logic behind synchronous machine, we'll get. In case of DC machine, where omega s is the angular frequency of the stator, speed of the magnetizing pole, stator's magnetizing poles. Omega r is the, see, mathematically, omega s equal to 2 pi fs, omega r equal to 2 pi fr, right? Now question is, in case of DC machine, what is the essential condition to get non-zero speed? If speed is finite, you can understand that inherently there is a torque production is there, right? This is important. This parameter is so important with respect to customer point of view. As an electrical scholar, you need to take care. As an electrical scholar, these two are under your control. Am I correct or not? These two are under your control. By regulating these two, we can able to control the speed based on the requirement. In DC machine, right, what we are doing intentionally, we are maintaining supply frequency Fs0. If Fs is 0, what is happening? If Fs is 0, stator frequency is 0, then what about omega s? 0. If omega is 0, what is omega m? Omega m and omega r both are same. What is omega r? Omega r is nothing but Fr. It is directly proportional to Fr. What is Fr? See, n equal to 120 f by p. This is the standard mathematical expression for speed. Can I ask one question here? Important question. It is related to electrical engineering only. All are in electrical. What is frequency? What is the definition? There is a standard definition is there for frequency. What is the definition for frequency? No. Whatever we are learning in class, standard definitions we should not discuss here. We have to think in other way, beyond. See, frequency is nothing but relative motion. You got my point? Frequency is nothing but frequency they will decide based on the relative motion between the magnetizing flux and conductor. How frequency will decide? Based on the relative motion. Based on the relative motion between the physical conductor and magnetic circuit, they will decide the frequency. Why brushes? DC machine, why brushes always will operate with zero frequency? What is the reason? In case of DC machine, brushes are always operating with zero frequency. What is the reason? The relative motion between the brushes and magnetizing poles are zero. Both are with respect to each other zero. Relative motion is zero. That's why brushes are always operating at zero hertz. You got my point? That's why with respect to brushes, current voltages after commutation action always 0 hertz. Clear? Understood? Now, see here, in case of DC machine, because of commutation action, right, we can able to maintain FR is exactly matching with NR. So because of this reason, if NR is finite, automatically omega m is also finite. If omega m is finite, customer feel happy. You got my point? So to get required speed in case of DC machine, intentionally, right, we are maintaining stator frequency 0. If stator frequency is 0, based on this operating, right, speed of the rotor, we can decide frequency of the rotor. Frequency of the rotor and speed of the rotor both are same. FR is directly proportional to NR, right? So NR and omega m both are same. Mechanical speed and electrical speed both are same in case of DC machine. You got my point, right? Electrical frequency and mechanical speed both are same in DC machine. But come to induction motor. In case of induction motor, we cannot access rotor bar. Am I correct or not? Rotor frequency is not in your hand. It is simple induction principle. Based on the induction principle, what will happen? Your rotor frequency is FR. It is SFS. Right? So, right, stator frequency is also finite. That is omega s. Omega s minus omega r we are maintaining to get finite amount of the speed because of induction principle. Because of the slip, we are maintaining this condition so that we are getting speed. What is omega r? Omega r is nothing but angular frequency of the rotor current. Omega s is angular frequency of the stator currents. By taking this difference, you will get required speed based on the customer. This is what we are doing in the induction motor system. Now come to synchronous machine. In case of synchronous machine, what we are doing? Throughout the operation, to satisfy the customer, intentionally we are maintaining FR 0. If FR is 0, then what about omega m? Speed of the rotor is matching with omega s. That's why it is called synchronous machine. Speed of the rotor is always at any instant of the time it is matching with omega s. If you want to operate your system in synchronous mode, essential thing is your rotor frequency must be 0. If it is a 0, then omega m is matching with omega s. You got my point? So that's why in case of synchronous machines, rotor poles are excited with 0 hertz. If it is a 0 hertz, then only we can bring the omega m to omega s. This is this standard mathematical expression for all. This equation is applicable for all machines. So as an electrical scholar, if it depends on the universal expressions concept, we can easily understand. We can easily compare the behavior of the each system so that finally we can derive the conclusion. Based on the conclusion, we can easily identify the application. Our target is the application, right? As an engineer, we are not focusing on the application. Simply we are working independently. That is the issue with present research side. There are two things are there. One, let them that there are two students are there in the class. One student is doing project based on the customer need. One student, he will do excellent product, but it is not useful to the customer. Idea is very good, excellent. Product is also very good. But thing is, it is not suitable for application point of view. But a student, idea is simple, effective, right? It is not much innovation is there in that product, but thing is that product is effectively utilized to the customer. Definitely a student will success in the market. You got my point? So whenever you want to do some research or whenever you want to find something, first top priority is you need to get the need from the customer. Once you know the need from the customer, right? Next we can easily summarize the problems. We can easily keep the problems in descending order. Seriousness, first you have to give top priority for the serious issues, right? After that, you can ignore the minimum, right? Based on the ranking, we can decide the order of the problems, right? This is, see, next, this is this topic. This is our main focus on today's session, right? After that, what is time? 4, 5 minutes, 2 minutes. After that, I will give break. So see, if possible, you can, there are some PowerPoints are there, you can charge your batteries. We'll try to develop the model now. 4:10 to 5:15, we'll try to do exercise on the DC motor characteristics, extracting the DC motor characteristics through the mathematical model. After that, transformations also we'll try to focus, right? Power variant and magnitude invariant, these two concepts we'll try to understand, right? After that, I will see, after session, I will try to share a video lecture to everyone, induction motor model, right? You can try yourself. Why? Because see, first initially we'll try to apply FOC to induction motor, right? Later we'll apply FOC to PMSM machine. Directly, if you go to the PMSM machine, it understanding very difficult. Slowly, step by step, we'll go. Clear? Now, see here. What is the? There is a common point. Is that if you observe these 3 diagrams, there is a one common point. Is there? What is the common point among these 3 waveform? See, even if you take this one, this is about natural system. Your natural system is always in AC. Your natural system input voltage is always AC. Why? Why we need to apply sinusoidal signal? There is a logic is there. Why we need to apply alternating signal across winding? Why we need to apply alternating signal across the stator terminal? Reason is your winding is in stationary. Naturally, all stator windings are stationary. You got my point? This is a very important point. Your coils are stationary, your winding is stationary. You need to apply alternating signal, right? But with respect to control point of view, what we are doing is, without losing any property, we are rotating winding, right? We are assume that winding is rotating, so that what will happen? Required voltages, required currents are converting into DC. Naturally, all windings are in stationary. Stator coils are stationary. But control point of view, what we are doing by applying these techniques, right? We are rotating the windings. Artificially, we are rotating, so that required voltages, required currents will converted into DC. If currents or voltages are in DC nature with respect to control point of view, your job become very simple. You need to concentrate only on magnitude control. If it is AC, you need to take care about magnitude as well as phase. You got my point? That's why these transformations are so important with respect to control point of view. See, practically, even if you take BLDC motor, SRM, PMSM machine, induction motor, right? All windings, right? Whatever windings we are exciting, all are stationary. Physically, there is no movement. Right? So that required shape of these signals, required shape of the electrically required shape is sinusoidal signal is required. Right? Whenever you apply this 3-phase voltage across your motor terminal, what will happen if you take induction motor? This is the nature of torque generated by the machine. You got my point? This is about torque versus speed characteristics of the machine. Right? What is Clark transformation? What is Clark? Clark is nothing but 3-phase to 2-phase stationary. Right? Nothing but, see, still your winding is your in complex plane, still your windings are 2-phase windings are stationary. Right? In case of 3-phase, this is about your windings. Right? In case of Clark transformation, what they are doing is they are taking, instead of 3-phase, they will take 2-phase system, right? With stationary coils. Your coils are stationary. Still, speed is 0. This is nothing but Clark transformation. In Park transformation, what they are doing, this winding they will rotate with particular speed. How much speed you will get clarity after completion of field orientation method. How much speed with how much angle with respect to particular angle, right? If you take care about the position of the winding, definitely we can change the characteristics of the machine with respect to control point of view, right? Now here, see, thing is whether your coil is, whether your reference person, now this is our reference person, whether, see, now reference person is sitting here. If person is speed is 0 or person speed is some finite or arbitrary speed, irrespective of the speed of the person, the behavior of the torque profile will not change. This is a very important point, right? You got my point? See, even if you take reference person, speed is 0 here, or person is rotating with omega equal to omega a, some arbitrary speed, with respect to this person, with respect to this person, or with respect to this person, with respect to three-phase system, or two-phase stationary person, or two-phase rotating person, if you calculate torque generated by the machine, in all cases you will get same behavior. Same profile you will get. Property will not change. Information, you will not lose any information. But thing is, reference point speed is, reference person speed is regulating, right? See, issue is with Clark transformation, advantage is number of variables are coming down. But still problem is, still your variables are in alternating nature. This is the issue. That's why later they have proposed Park transformation. By adopting the Park transformation, two-phase variables we can convert it into DC. If you want to change the voltage behavior from AC to DC, right, essential thing is you have to assume that your winding is rotating at synchronous speed. If winding is rotating with same speed of the magnetizing poles, then signals are required signals, voltages or currents are required current or required voltages are in DC nature. You got my point? So this is so important. Even person is rotating or stationary in two-phase or three-phase with more number of variables. See, whatever behavior you are getting with 7 state variables, with less number of variables also you will get same behavior, right? Behavior will not change. Only complex, see, number of variables involved in the system will decrease. If you want to improve the profile, what it required? Essentially, you need to take proper power electronic model. This is a very important, right? By selecting the proper power electronic model with transformation technique and, right? See, so these are all the methods. Whenever you want to improve the steady state profile as well as dynamic response, you have to go through these 4 points. No option. We don't have any freedom. Whether it is a PMSM machine or induction machine or, right, any special machine, we don't have any freedom. We have to go through these 4 points. First one is, what is the first point? First, we need to understand the behavior of the actual system through mathematics. This is what we are doing now, initially. So what is the outcome of our session? My target is selecting vector control technique to eliminate the nonlinear. This part, at the end of this course, you will get clarity. So in today's session, my job is, I am trying to explain the how to understand the behavior of the various electrical machine, how to apply transformation technique to reduce the complexity. These 2 topics I am focusing in today's session, right? In next session, I will try to, by using hierarchy, by taking care about the control hierarchy, right, with proper power electronic model, how we can improve the dynamics, we'll try to discuss in detail in the next session, right? After break, we'll try to focus on, right, see how to develop the mathematical model of the DC machine, right? Then after that, you decide. If you are very familiar to the DC machine, directly I will go to transformation. Mathematical model of DC machine or mathematical model of transformation? Which one will start? You decide, participants. You know mathematical model of DC machine, right? How many know? Can you raise your hand if you know the, how many participants know the mathematical model of DC machine? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. then what we'll do? Tell me. We'll develop 10. I will not spend more time. See, my problem is my lectures are going very slow. My teaching method is very, very slow. I don't know how many participants are following or not. Real. Any questions before break? If you have any questions, you can ask. Everyone is following. Fine, clear. Fine. Okay. Any questions are there? You can ask. Then see what I will do is first I will focus on the transformation. Why? Because it is no more related to the mathematical model of the system. It is completely, concept is different. I will write equations, same equations you have to develop in your simulation file. You will get result, right, for magnitude variant and power invariant condition. Particularly magnitude invariant condition, power invariant condition is so important for power quality applications. Whenever you want grid connected inverters, whenever you want to control real power or reactive power effectively, right? See, magnitude invariant condition is so important. So, sorry, power invariant. Magnitude invariant condition for drives application, it is sufficient. By applying magnitude invariant condition, we can able to extract the torque characteristics without losing any property, right? Okay. Anyone want to ask? I'm telling windings are stationary. If coil is stationary, see, say, if coil is stationary, why we need to apply sinusoidal? Relative motion. Okay. What is the benefit you will get? Okay, if you maintain relative motion, what you will get? See, if you want to convert the energy, what is the significant parameter in the circuit? Back EMF. Back EMF is so important for energy conversion. If back EMF is less, what is the issue? Machine will take more current, losses are more. See, based on the back EMF and current, we can decide how much energy is developed in the rotor, we can decide. Power developed in the rotor is nothing but back EMF into current only. But issue is, if back EMF is less, current is more, heating effect is more. If back EMF is more, current is less, right? Advantage is we can operate more period. If you want, that's why as an electrical scholar, you need to take care about what is the nature of back EMF. Based on the back EMF nature, we can decide the reliability of the system. That's why BLDC motor morning, see, one participant, I think they ask questions. What is the difference? Why BLDC motors are not adopting in transportation system? BLDC motors generally they are adopting for low power drives. Reason is current is not sinusoidal. Heating effect is more. Whenever you want to use BLDC motor effectively, you have to reduce the power levels. By reducing the power levels, right, without heating effect, we can operate more period. Main advantage of the BLDC motor is design is simple. Concentric winding is very simple. Coil replacement is also very simple. Control is also very simple. But PMSM machine, winding design, distribution factor, pitch factor is very difficult. Designing the distribution winding is more complicated than the concentric winding, right? But advantage is your back EMF becomes sinusoidal, current is sinusoidal. If current is sinusoidal, heating effect is less. These are all the advantages, right? Next, important thing is if coil is stationary, you don't have any option, you need to apply sinusoidal. If coil is rotating, then you need to apply DC. If it is a DC, even coil is rotating, with respect to rotating coil, your signal is looking like sinusoidal. You got my point? Your back EMF, energy conversion is taking place, right? So after the break, we'll try to concentrate on how to develop the transformation technique initially, right? After that, after completion of this task, then we'll try to focus on mathematical model of DC machine, right? Then assignment 1 is induction motor model you have to develop by Wednesday. is fine. Wednesday or Thursday? How many students already they develop induction motor model? Can you raise your hand? Already you have developed, right? Sorry? 5 phase. Even if it is a 5 phase or 3 phase, we need to develop model in 2 phase on. How many students can you raise? Once again, 1, 2, 3, 4. 4. You have developed induction motor model. Okay. Only 4. Then assignment I will give. Other students can help. My scholars also they will help. I will give my scholars phone number, mail ID. You can contact through mail or phone. They will help. I will also help. Right? Anyway, I will forward equations. Only your job is you need to substitute the equation in MATLAB. You will get behavior of the system. Right? It is not a big deal. Right? First try to get the mathematical model of induction motor. Before coming to the next session, I will try to forward PMSM machine model assignment. I will explain the concept. Assignment is model you have to develop in your hostel. Why? Because see, please try to understand. Okay, now break time again. It will go up to 5:30. I will stop here. Okay, thank you. Here what I will do is, right, here I will take reference person. Right, now this is my requirement. I want to change the 3-phase vectors into 2-phase vectors. While converting the, see, whenever you want to change these vectors from 3-phase to 2-phase, right, you need to take common reference. This is very important. Reference person, thing is here, good thing is reference person. For understanding purpose, here I have taken reference person exactly in phase with A axis. At the same time, right, in this is about 2-phase. In 2-phase, right, vectors I will take in phase with alpha is in phase with reference person. This is also one advantage, right? Right, this is about beta. Now with respect to this person, now we'll try to identify the transformation matrix. This matrix is so important. Conversion matrix is so important while transferring the signals from variables from 3-phase to 2-phase without losing any property. Right? So here what I will do is, with respect to this person, what is the mathematical model for A? With respect to this person, how we can represent A? Let us assume that this is FA, FB, FC, this is F alpha, F beta. A phase MMF, B phase, C phase MMF in 3-phase, F alpha, F beta in 2-phase. Now, how we can express net MMF produced by 3-phase with respect to this person? Whenever you want to calculate net MMF with respect to this person, reference person, common person between 3-phase and 2-phase, right, you need to take care about what is the space displacement angle between reference person and individual vectors. Now, so from this, with respect to this person, right, in 3-phase, net MMF is FA into e power j0. Why e power j0? Space displacement angle between vector and reference person is 0. That's why angle is 0. Now, next plus FB into FB leads the reference person. Reference person is here. FB leads the reference person by 120 degree. FB e power j 120. Clear? So plus FC e power j plus 240 or minus 120, both are same. So this is the mathematical model, right? This is the resultant MMF produced by the net MMF produced by 3-phase system with respect to this person, right? So this MMF, and so with respect to this person, what is F alpha? F alpha into e power j 0 plus F beta e power j 90. Solve this equation. Do first. Tell me what are the real components, what are the imaginary component. Now here thing is FA, FB, FC are known values. Please try to understand. Fa, Fb, Fc are known values. F alpha and F beta are unknown values. Multiply, solve. See what is mathematically, what is e power j, what is e power j? Theta. Cos theta plus j sin theta. Right? So, Fa into cos 0 plus j sin 0 plus Fp cos 120 plus j sin 120 plus Fc cos 240 plus j sin 240 equal to F alpha cos 0 plus j sin 0 plus F beta cos 90 plus j sin 90. What is the advantage here? Tell me. See, here thing is, next one more important thing is FA, FB are under your control. FA, FB practically these two components are not existing in the actual system. You got my point? But without losing property, with respect to control point of view, three-phase variables, we can convert it into two-phase. While converting the variables from three-phase to two-phase, if you take space displacement angle between these two is 90 degree, advantage is, what is the advantage with respect to control point of view? What is the advantage? This one, see, this is under your control. This is based on our convenience. We are taking alpha alpha and F beta with 90 degree delay. If you take less than 90 degree, what is the issue? Later you can check. Mathematics, it is mathematics only, right? If you take less than 90 degree, what is there? See, calculating F alpha and F beta in terms of Fa, Fb, Sc, Fc will become more complicated. Why? Because decoupling is not possible. By taking 90 degrees between F alpha and F beta, we can calculate F alpha, F beta effectively. Within 2 steps we can calculate. Otherwise, if it is less than 90 degree, if you want, you can try. Real side F alpha and F beta will enter. Imaginary side also F alpha and F beta will enter in the equation. Calculation is more complicated. See here. Now, see, if it is a 90 degree, what is the advantage here? Tell me. If it is a 90 degree and 0 degrees, one vector is in phase with reference person, another vector is perpendicular to the reference vector. These two are artificial signals. These two are so important with respect to control point of view. Without losing any property, right, what we are doing is we are converting the signals. Now, while converting the signals, you need to take care about the space displacement angle between the two vectors. If it is a 90 degree, advantage is, now here sin 0 how much? 0. If it is a 90 degree, F beta is 90 degree away from the reference person, advantage is this component becomes 0. You got my point? So, with respect to this equation, imagine a real component will eliminate it. With respect to this equation, imaginary component will eliminate it. You got my point? So, from this equation, separate real and imaginary component. Do first F alpha and F beta, separate real and imaginary component. Fa, Fb, Fc. So, cos 0, cos 120, cos 240, sin 0, sin 120, sin 240. You got my point? But thing is, this is not a symmetrical matrix. See, technically, right, these equations are fine. Based on our assumption, based on, see, our two-phase vector position, you got this equation. But mathematically, this is not a symmetrical matrix. That's why you have to take something else here. This is a way, these values will play key role whenever you want to adopt magnitude invariant and power invariant condition. You got my point? See, in today after session, I will forward one video lecture, go through it, you will get clarity about transformations. For all participants, I will forward, go through it, you will get more clarity about the significance of this third row. Right? Everyone understood here? But in textbook, what they are doing is reference person, they are not taking in phase with A axis. Let us assume that reference person is leading or lagging. Issue is what is happening, theta will enter. Some angle is entering this equation. Right? See, that's why if it depends on the space vector concept, right, extracting the transformation matrix, it is not a big deal. So example, see, by taking this example, you can understand what is the significance of this complex vector representation. You will get more clarity. If it depends on the complex vector representation, e power j operator, it is not a big deal to extract the transformation irrespective of the reference person. If reference person is somewhere else, also no issue. Right? This is FC. Now here thing is this is F alpha, this is F beta, right? Now reference person is here. Our reference person is here. You got my point? Understood? Now tell me. So this is about theta, space displacement angle. Reference person leads the x-axis by theta. Now in this case, anyone please tell me what is the mathematical model for transformation matrix with respect to this reference person. Please try to understand, with respect to reference person must be always in phase with two-phase frame. You should not take reference person on three-phase. Why? Because controller is designed based on the two-phase reference frame. That's why reference person must be standing in phase with two-phase axis, so that what will happen, number of variables will come down. Now if reference person is sitting here, then what is the transformation matrix? I will see. Now person, with respect to this person, FA is lagging or leading? Lagging. How we can express FA? If it is lagging with theta, how much angle? So yeah, simply your job is FA you need to multiply with e power minus j theta. You got my point? FA, if you multiplied with e power minus j theta, you will get clarity about what is the effect of FA on reference person in D axis as well as Q axis. You will get clarity. You got my point? Effect of FA on alpha axis and beta axis, you will get clarity if you multiply with e power j theta. Right? Next, what about FB? So, very good. 120 minus theta. See, last day there is a this one quiz is there, right? See, I will not ask the question beyond the whatever we are discussing in the regular sessions. We are not asking any questions beyond the class. If you put more attention in the sessions, definitely you will get good score in the examination. Feedback, before giving feedback, you have to write, you have to go through the examination, right? But there is no grade system, right? You got my point? We will not decide any grade. Only this is only for understand the participants' characteristics. That's why in browser itself I have not floated any grade option also. For other GIAN program, they are offering grade sheets also. Right. Please start on. Within 5 days, it is very difficult to understand the concept in detail. At least, see, if you understand the philosophy, it is fine. Later, if you follow this philosophy, definitely your problems, it will solve. Right? So, FC e power 240 minus theta. Fine. Or 120 plus theta. Both are same. So, what is the equation? This one is equivalent to F alpha plus J F beta. So, finally, in two-phase side, you will get one real and one imaginary component if you take 90 degrees space displacement. That's why this angle is so important. This one must be 90 degrees. If it is a 90 degree on two phase side, only two variables are there. Sorry, only one variable is there on real component side and one variable is there on imaginary side. Right? Separate. If you solve this equation, you will get f alpha, f beta equal to, see, cos of theta, cos of 120 minus theta, cos of 240 minus theta, next minus sine theta, sine of 120 minus theta, sine of 240 minus theta. Clear? This is the transformation matrix. But issue is, now here big challenging is, see, what is the base for transformation? I want to ask one important question. Before writing equation transformation matrix, I want to ask one important question. What is the base for any system? What is the base for transformation system? They will take voltage as a reference, or current as a reference, or flux as a reference. What is the base for transformations? MMF. MMF should not vary. Whatever MMF produced by the three-phase system, same MMF you need to take care in the two-phase system also. If you satisfy this condition, right, you will get same behavior of the system. Whatever behavior, whatever system is offering characteristics in three-phase, same characteristics we can extract. Even number of variables are less in two-phase, same behavior we can extract with less number of variables. That is the strength of MMF. See, maintaining constant MMF in two-phase as well as three. Whatever MMF strength is there in three-phase, same MMF we need to produce in three-phase system. Like that, you need to take turns ratio. Here, this one, this is the multiplication factor. Why? Because number of phases are more in three-phase, MMF strength is more. What is the resultant MMF strength? 3 by 2 FM. But in two-phase, what is the net MMF? FM, peak value. See, in three-phase system, net MMF equal to 3 by 2 FM. What is FM? FM is the peak value of the individual phase signals. Now, two-phase system, FM. What is the difference between three-phase and two-phase? What is the multiplication factor? What is the difference between these two? 1.5 is the difference. You got my point? So there is a difference is there, net MMF. If you balance, if you take care about this one, see, important thing is MMF is nothing but number of turns into current. You need to take care about the current magnitude as well as turns ratio. By taking care about the turns ratio and current magnitude, we can maintain constant MMF after conversion also, right? So what is my request is, I will write equation, I will write formula. You have to substitute in MATLAB and verify whether magnitude is changing or not, whether power is changing or not, we can check, right? So one thing is, so what is the logic behind magnitude invariant and power invariant? I will share video lecture today after session. By 8 o'clock I will share, go through it. You will get more clarity about magnitude invariant and power invariant. Okay. So F alpha, F beta, see, 2 by 3. This is a very important thing, 2 by 3 multiplication factor, right? If you take 2 by 3 multiplication factor, what is the advantage? What is the thing? Transformation matrix. Whatever matrix we discuss, that matrix you have to substitute K matrix. Then here you have to take three phase variables, FA, FB, FC. Then this transformation is called magnitude invariant, right? Next come to F alpha, F beta, right, equal to square root of 2 by 3 into transformation matrix FA, FB, FC. This is nothing but if you multiplied with the transformation matrix with square root of 2 by 3, why 2 by 3 in magnitude invariant, why square root of 2 by 3 in power invariant, in detail, right? You will get more clarity after going through the video lecture. I will share after this class. Immediately I will give permission, you can access, right, through your email IDs, right? This is about power invariant. Now I will try to show the equations, same thing, take photo and try to implement in your system and verify the result, right? Up to here everyone, anyone having doubt? Any doubt? See here, take first waveform. Let us that what is my request is, in simulation you need to take 3 sinusoidal waveforms, right? Take 3 sinusoidal waveforms from the library direct itself. You can take frequency 50 Hz and magnitude 1, right? After that multiply the signals with 2 by 3 into, take theta 0. If you take theta 0 you will get cos 0 equation, same equation you can take. Later I will tell from where this theta you will get. That is very important in FOC, right? By using FOC, theta we are inducing in the transformation technique, so that what will happen, your system, right, system order equation will become from 4th order to 2nd order. FOC is nothing but combination of transformation, field orientation and V by F. There are 3 logics are required. If you want to change the characteristics of induction motor from 7th order to 1st order, you need to take 3 concepts. One is transformation, another one is orientation, last one is V by F. By adopting these 3 logics, we can change the characteristics of the machine from 7th order to 1st order in case of induction machine. In case of PMSM machine, 4th order to 1st order it will change, right? So here, now tell me what are the conclusion here. Otherwise I will take just a minute. I will take one more. So this is a very important slide for net power invariant condition and power invariant condition. You need to multiply with transformation matrix with this transformation matrix. You need to multiply with square root of 2 by 3, right? Then in that case what will happen, net power will not change. What is net power? Whatever power is resultant power generated by the A phase, B phase, C phase in 3-phase system, if you calculate resultant power, that power exactly matching with power generated by the alpha axis coil and beta axis coil. If you add together, then 2-phase net power and 3-phase net power will balance to each other. So that, see here, take case 1. In case 1, see these signals are 3-phase signals, right? Right, these signals after converting Clark transformation matrix, after now here we adopted magnitude invariant or power invariant. Check This is about power, 3-phase net power, 300 volt amp, right? This is 3-phase system, this is about 2-phase system. This is magnitude invariant or power invariant. Power is constant, check. 3-phase system, what is the power, net power? This power you will get after adding, sorry, VA IA plus VB IB plus VC IC. Instantaneous voltage and instantaneous current, if you multiply you will get instantaneous power. Net power is constant in 3-phase system. Even if you take 2-phase, so V alpha I alpha plus V beta I beta, if you calculate, it will give same amount of the power without losing any property. Whatever power generated by the 3-phase system, same amount of the power we can produce in 2-phase system also, but necessary condition is you need to take square root of 2/3. Right? Okay. Another example is for phase power invariant. For phase power invariant or magnitude invariant, both are same. For phase power invariant, nothing but, right, magnitude, it will not change. Check here, this is case 2. Another case, magnitude's peak, you can check. In case 1, power is not changing, net power is constant, but if you verify individual peaks, right, it is getting effect. Now, in case of magnitude invariant condition, right, 3-phase peak voltage and 2-phase peak voltages, V alpha peak, right, VA peak, both are same. Nothing but magnitude is not getting effect. For phase power is also checked, for phase power it is not changing. But if you add net power, it will get change. Net power is different, 1.5 times less. Please start understand. See, you got my point? So, see, this is the numerical example. Instead of numerical example, so what is my suggestion is, take, so better first initially you can, I will show the diagram, try to implement same thing in your system. Write down. We'll try to focus on we'll take this equation, net power invariant will take, right? So I alpha I beta V alpha V beta is square root of 2/3 into transformation matrix. So in transformation matrix, if you take theta 0, cos 0 1, cos 120 minus 0.5, cos 240 minus 0.5, next sin 0 0, sin 120 root 2/3, sin 240 minus root 3/2, right? Now take this equation and solve in simulation and tell me same results you have to get. Take this equation, do first. Simulation block for 3-phase to 2-phase. Condition is power should not vary. Net power invariant condition you have to take. First take this picture. Otherwise, instead of writing, you can take photo and do simulation. Writing blocks also it is fine. If you want to write the blocks, if you want to draw the blocks, also fine. Sir, in some papers they have given transformation matrix in different way. No issue. You forget about what is their representation. Where is the reference point is so important in transformation method. What is the speed of reference person is also so important. Fine. So for V alpha, V beta, I alpha, I beta, these are all the equations. So I alpha is square root of 3/2 IA, right? What is I beta? I beta is, so what is my request is solve yourself. Take, see, in this case, VA, VB, VC are known values, IA, IB, IC are known values. Unknowns are I alpha, I beta are unknown, V alpha, V beta are unknown. So, by using transformation matrix, we can derive the unknowns in terms of known values. To find the unknowns, right, we can derive the equation, we can solve the transformation matrix so that you will get see. I will write one for current, I will write remaining thing for I alpha, I will write here remaining thing you have to do. So from this equation, so I alpha, I beta equal to transformation matrix 1 minus 0.5 minus 0.5, here IA, IB, IC are known values, right, 0, square root of 3 by 2 minus square root of 3 by 2. From this equation, if you solve, what is I alpha? From this equation, from this matrix here, 2 by 3 is there, square root of 2 by 3 is there. What is the reason behind 2 by 3? You will get more clarity after going to the video lecture. I will forward video lecture, then you will get more clarity. Right? I alpha equal to square root of 2 by 3 into, so 1 into IA minus 0.5 minus 0.5 into IB plus minus 0.5 into IC, so minus of 0.5 into IA, IB plus IC. Clear? So what is IB plus IC? IB plus IC nothing but minus IA. Clear? You got my point? See, IA plus IB plus IC is nothing but minus IA we can write here. These two, IB plus IC we can replace with minus IA. Then you will get finally I alpha equal to, what is I alpha? In magnitude invariant condition, sorry, power invariant condition, I alpha is nothing but square root of 3 by 2 into IA. Similarly, V alpha equal to square root of 3 by 2 VA. For currents and voltages, same multiplication factor you have to take care, right? Similarly, I beta, from the equation I beta is square root of 2 by 3, see, 2 by 3 in, plus square root of 3 by 2 IB minus IC. This is the equation. So from this equation, these two will cancel, right? Finally, what is I beta? I beta equal to 1 by root 2 of IB minus IC. This is about I beta. So I alpha, I beta are known. Similarly, same V alpha and V beta we can write. Right? Now, this is about simulation. Now, these three are unknowns. Let us assume that V alpha, VA, VB, VC are known values. If you want to get V alpha, what it required? You need to multiply with square root of 3 by 2. Right? Clear? Now, V beta and VC, how to get V beta? V beta is nothing but 1 by root 2 of VB minus VC. This formula you have to write. So here VB minus VC, right? Then VB minus VC, if you multiply with 1 by root 2, you will get V beta. Clear? So first you need to calculate V alpha and V beta, then take sinusoidal currents. Here peak value you can take, what is my request is, you can take peak is 200 volts. Peak 200, frequency you can take 50 Hertz, right? Time delay between A phase to B phase 120 degree you can take 120 degrees or 2 pi by 3 radians. Here this one current you can take IA, IB, IC you can take peak value 1 amp, right? Solve this block, then you will get, see, if you add V alpha into I beta plus V beta into I beta, you will get net power in two phase. This power and see VA, IA plus VB IB plus VC IC. If you add for phase, A phase power, B phase power, C phase instantaneous power, this power and this power both will match. That results you have to show before closing today's session. Do first. So this is about simulation. These 3 are sinusoidal signals you can take from the MATLAB directly. Peak value, this all are VA, VB, VC. This IA, IB, IC you have to take. Then see, you no need to implement whatever diagram is there in slide. Same thing you no need to implement. You can write another code also. So here you will get net power in 3 phase. Here you will get for phase power, net power in 2 phase. 3 phase net power, here you will get 2 phase net power you will get. Finally, this is nothing but this is this signal, this is V alpha, I alpha, this is V beta, I beta. So V alpha, I beta you need to multiply, V alpha, I alpha you need to multiply, then you will get net power in 2 phase. Next here VA, IA you need to multiply, VA, IA you have to multiply, you have to get VB, IB, you have to get VC, IC, you have to get, add all 3 per phase powers in 3 phase, then you will get net power. These 2 waveforms, if you observe, both will give same result. If you take care about the multiplication factor for transformation matrix, square root of 2 by 3 if you take, net power will not change. See here, check, there is no change in the net power. Output power is same. Power will not change. But here, verify what is the peak here. How much peak they have taken in 3 phase? 220. But after converting the signals from 3 phase to 2 phase in power variant condition, power invariant condition, how much? It is closely to 300. Magnitude it is getting effect, but power it is not getting effect. Right? So open your system, do fast, then we'll wind up today's session. You can take randomly. See, you no need to produce same 300 all time. Right? You can take magnitude of the current whatever you want, no issue. But here voltages are known. Currents you can take 1 amp, no issue. Take 1 amp, calculate and tell. Anyone having doubt, you can ask, my scholars are there, they will help. Anyone having doubts, raise your hand, they will help. Just raise your hand, any doubts are there, they will help. My scholars are there, 3 scholars are there. See, one more important thing is, it is not a technical related. Any issues are there in hostel accommodation, kindly inform me. We'll try to provide minimum at least. We'll try. See, minimum facilities I will take care. Why? Because for Dasa hostel, I am the warden for Dasa hostel, right? So caretaker, I can manage caretaker. They can shift the, now it is recording, I should not talk anything. Unofficially, I can change the room also. Dasa hostel or any issues are there in 13th block, ladies hostel? Is it fine, clear? See, it is not permanent. My request is, it is only temporary. Try to focus on our objective. This is our main objective. Any serious issues are there, inform to me. I will change. I will ask wardens dynamically, they will change the room. Any issues are there with power should not vary. Any doubts are there, you can ask. You are getting, you got, you are get, huh? Rajnikant ఒకసారి. See, actually, she is BTech student. She is doing electrical engineering in Nagpur, third year student. Tomorrow I will get. Huh? Tomorrow I will ask.
See, I will share the video lecture for how to develop the mathematical model for DC machine. First, I will share. Then after that, what is the logic behind square root of 2 by 3 and 2 by 3 multiplication factor. Also, there is a video lecture is there. I will share. See, night time about dinner. You can have dinner in institute messes. I think cost is not more than 80 rupees. I think per day. You can have. Otherwise, even if you go outside, also you will get. But thing is, in institute messes and Kalam Hall, right? Quality of the food is very good. Taste not up to the mark, but it is hygienic. Your health will not get disturbed. If you go outside, taste very good, but health may get disturbed. Take care. Next 25th, it is a holiday institute. Even messes inside, I think Kalam Hall is completely closed on 25th. Right? Take care about breakfast, lunch. Right? See, particularly those who are staying in Dasa hostel, you can have breakfast and lunch in IFC A and B. Both messes are there near to Kalam Hall. Sorry, near to Dasa hostel, walkable distance. I think less than 100 feet. Right? So breakfast price is 30 rupees. Right? Lunch 50 rupees. 50. 30, 50. Night also 50, I think. Not more than 150 rupees per day. Anyone having doubt, you can raise your hand. This is about function block. This block is available in MATLAB. This is function block where you can write program. You can write code. If you go through the user defined blocks in the library, you will get function block. If you are very good in programming, directly you can take script file and you can write program also. That is also fine. Otherwise, you can take embedded file also. You can write program. It is fine. See, any issues are there, I'm requesting once again, I will come. I will take care, particularly in hostels. Any issues are there, inform to me, right? We'll guide. Can I ask one question? You can continue in between, I will ask. Right? What is the significance of switching frequency? How they will decide the switching frequency of power electronic model, see in drives application or converter application, any PV solar cell applications or drives application. What is the base for deciding the switching frequency of power electronic model? Switching frequency is very important. No. Simply we cannot select the switching frequency randomly. There is a cause, there is a reason. Why transformations are required here? Actual system is creating issue. It required need. What is the need with respect to three-phase system? No. Magnetizing current and low torque producing component, flux producing component, both are flowing in the same path. To get information, we are adopting transformation. By adopting transformation, what will happen? You will get clarity about what is the strength of magnetizing current, what is the strength of torque producing component you will get. Right? Clear? Then how we can decide switching frequency? It is also based on system characteristics. Everything, please try to understand. That's why I'm telling as a scholar, whenever you want to understand the concept or whenever you want to control or whenever you want to develop model, important thing is you need to understand the actual system behavior. If you know the actual system behavior, if you know the system characteristics, right, how they will decide switching frequency. What is the base? In drives application, why switching frequency is not going beyond the 3 kHz? 2 kHz is sufficient for drives application. What is the reason? See, the advantage of the drive is there is a sufficient filter is there, winding inductance is there. If there is a physically there is a sufficient inductance is there, you no need to go for high frequency. Your machine itself acting as a filter. Even if you operate low frequency, your harmonics are appear at lower order. By using, see, your machine itself will take care about the lower order harmonics. But in case of LED light application or PV application, reason is your system inductance effect is negligible. That's why to maintain current in continuous mode, this is very important. To maintain the current in continuous mode is a very big challenging for engineering control point of view. With respect to control point of view, if switching frequency is less, what is the issue? If switching frequency is less, time period is more, switching time is more. If switching time is more, there is a possibility is there entering the current into discontinuous mode. Once current is entering in the discontinuous mode, issue is speed, it will get effect. Speed drooping will increases. Your controller will not work effectively. Right? That's why you need to operate your drive always in continuous conduction mode. If it is in continuous conduction mode, see speed drooping, operating speed of the drive, even if you apply the load, speed will not change. Speed regulation become very good. Is switching frequency, you have to take care about the switching frequency, definitely speed regulation is very good. If drive is not operating in continuous, not operating in discontinuous mode, there are a lot of benefits are there. But in case of LED drive application or PV solar cell application, the nature of the system, if you take LED light, LED system or solar system, effective inductance is negligible. That's why they are taking switching frequency more than 100 kilohertz. If switching frequency is more, time period is less. Advantage is if you take less time period, your current it will not enter into discontinuous mode. To avoid the discontinuous mode, they are deciding the switching frequency based on the actual system inductance.
You got my point? First we should know actual system inductance, based on inductance only. Right? Complete, at least one student, one participant. How many participants has completed? Can you raise your hand? Take simple sinusoidal signal VA, VB, VC. Multiply with square root of 3 by 2. Do fast. Now already 5:30. We need to wind up. You have taken photo of this slide. Okay. Take photo and try in your system. Otherwise, can you complete by tomorrow? This part you can complete. Can you complete by tomorrow? How many participants got results? Can you raise your hand? You got, sir? Okay, very good. One complete. You have completed. Very good. You have completed. Okay, very good. If anyone need help, you can take inputs from scholars. They will help. That's why before starting this session, GIAN program, I requested everyone, see, if you come with your own laptops, it is easy. We can exercise in hostel also, right? Can you see? Can you try in your rooms? Okay. Shall we stop here? Anyone having doubts, you can ask for today's session, afternoon session. Any doubts are there, you can ask. Right. In next session, my focus is on developing the control hierarchy. Right. I will try to explain what is the logic behind to extract the control hierarchy for electric drive. I will explain. So control hierarchy is common for DC drive, AC drive, special machines. Hierarchy will not change. It is a fix. Right? If you follow this hierarchy, definitely system performance will improve effectively. Right? My next topic is developing the control hierarchy for electric drive. It is on Thursday afternoon, right? Thursday morning, one slot is there, afternoon 3 hour slot is there. Can I stop here? If anyone want to ask, you can ask, then we'll wind up there. Otherwise. See, even getting delta X knowledge through this workshop also, it is fine. Delta X is also fine. Okay, thank you all. We'll meet. When is our session tomorrow? At what time? 9 or 9:30? Can you check tomorrow schedule? 9. Okay, fine. We'll meet by 9 o'clock tomorrow. So Kalam Hall, they will open by 8 o'clock only. So go and have breakfast by 8 o'clock. Come here before 9 o'clock so that we can start session at exactly 9 o'clock. Right? So morning completely. What are the topics here? Morning session, day 1, lecture schedule. See, tomorrow again, see fundamental concepts, and also next energy conversion and review of synchronous machine. There are 3 sessions are there, 9 to 10, 10 to 11, 11 to 12. Then after that, I will try to explain control hierarchy for electric drive. Then afternoon, Dr. Srinivas Rao sir will take care about
high power inverters for EV application. Then after that, same simulation, how to execute the different PWM techniques for multi-level inverters, he will explain, right? Okay, thank you.